New DeepSeek v3 just became the best non-reasoning model in the world, surpassing Grok 3 and GPT 4.5. And in this video we will learn how to understand it and code it from scratch. You will understand everything from the paper and the science behind it to writing the code. And you will have this whole file written and understood by the end of this course. From their multi-head latent attention mechanism that they contributed, we will understand it and learn to code it. We will understand the attention basics, rotary positional embeddings, their MLA, and many more concepts. From their mixture of experts architecture, we will understand gating, each experts, multi-layer perceptrons, and many other concepts. We will also learn how they parallelize matrix multiplications across GPUs. You can help me accelerate and spread AI progress for many people on Patreon. For just $5, you can help 200 people accelerate their AI progress and understanding by 2 to 3 hours. My goal is to do this full time so I don't need to have a different job and I can help a lot of people become AI scientists and engineers and understand AI a lot better. And now we will start with the multi-head latent attention, where I will just show you the formula and then I will start explaining attention from the beginning. Let's take a look at these formulas in multi-head latent attention. They seem complex, but they are very simple once you understand them. So let's start from this HT. This HT is just input embedding vector. So I wrote here token embedding vector, for example dog. So we have some token dog and its embedding vector. Length, I think in DeepSeek it's 7168. So HT is this embedding vector. And then we multiply that embedding vector with some matrix. Now what is this matrix and what does it do? Down, key, value. So when you see word down, which you can read about here, so this is where they explain that this is down. That means that this matrix is trying to make this vector smaller, because this vector, we will use this for future calculations that I will explain later. But we don't need to have this big, huge vector that has 7,000 numbers and has all of the information about this dog token. We can actually reduce this vector, and let's ignore all of this. Let's just get to the reduced. So this is the reduced vector. This has only 500 numbers. And this vector, you can imagine it as trying to keep as much information as possible from the big vector that's 12 times bigger, but just reducing it so we can compute it easier. So here in this formula, we take the big input vector, we somehow transform it with this matrix to get a small, very small vector that contains as much information as possible from this vector. So we try to remove all of the redundant information that's not so useful and only keep the best information. And during the training, AI will learn this matrix that will best convert this big vector to keep its most important information to this a lot smaller vector. I do recommend you take pen and paper and try to draw this yourself or try to explain this and see what you don't understand. Then you can always ask GPT and copy this text and ask about it. So I do recommend you try to keep up with understanding everything. Although I know it's difficult, it took me like 2 days just to understand, or maybe 1 day to understand this part and a bit of here, and maybe 2-3 days to understand this whole concept, even though I understood the concept of self-attention before. Now this vector, it's not just compressing this vector as best as possible. That's not the only goal. The goal is to compress, but also to compress and extract information that will help create key and value vectors later. Now, what are these key and value vectors that this matrix is trying to help create by extracting information? Here I have some example to show you what queries, keys, and values are. Let's say we have this sentence, the dog ran quickly around the, and for each we have a token vector embedding. So let's say these are tokens, although they are usually not, but let's just assume. And also in DeepSeek, these embeddings would be 7,000 numbers long, but here we have 3 for this example. Let's say, so this embedding, vector embedding, encodes the meaning of this word quickly. But in language model, we don't want this vector to just encode meaning of this word quickly. We want it to also encode in which context this word is used. So this is used to say that the dog ran quickly around the. So how do we add all of these other meanings, a little bit of them, of each, to create context around in this vector embedding? First, we will talk about this quickly vector. And we will talk about query. So we want to generate some other vector that's going to be query, and what it will do is it will explain to other vectors what kind of context this quickly vector is looking for. For example, it would be looking for ran, so it knows that the quickly refers to ran, but it wouldn't necessarily be interested in this word the, because the doesn't contribute anything to this word quickly. So when we create a query vector from this vector, it's going to basically say what this quickly vector is looking for, what kind of context. And later we will literally add meaning from this ran to this quickly. And we will add a lot of meaning from this ran word to this quickly, because this is a relevant word. And this word is not so relevant. So we will add 0 to only just a little bit of meaning. So how do we create a query vector? So we have this vector embedding, and we have some learned, model learns this matrix, and this matrix will convert this vector into a vector that I didn't write here. This is what it will look like. So this is matrix multiplication between these matrix, but we can just look at this vector, and it will produce this query vector. Usually this query vector is shorter, and maybe even a lot shorter than this embedding vector. And this query vector will communicate to all of the other tokens what kind of context this word quickly is looking for. This query vector is just for this token quickly. If I multiplied all of them with this matrix, then we would get a matrix as well here, each query corresponding to one of these tokens. But this matrix that converts token to query is always the same for every token, for everything. It's always the same. And LLM learns just one, and it converts. So this matrix, imagine it as learning how to extract information from the token that's going to be useful when you seek for context. So the information that explains what context the token needs. So we will do the same for key and value. We will have these two new things that you may not really understand, that I will explain. So it's called key and value, and they have their own separate matrices, and both of these matrices are always the same. So key matrix is same for every token, and value matrix is always the same for every token. And LLM learns these three different matrices, and when you multiply quickly token with key matrix, you also get some vector that's key vector for this token, and you also get value vector for this token. If you have this query that shows what this quickly token is looking for, what kind of context it's looking for, how do you now check what context this ran has, what context this dog has, what context this dog has? One way to check similarity between different meanings. As I explained, these vectors encode meaning, and this vector also encodes meaning. Now the difference, I will repeat again, sorry. The difference between quickly vector and quickly query is that this contains meaning of the word quickly, and this contains meaning of what kind of context the word quickly is looking for. Now let's look at the key. Key says what kind of context this token has. If somebody is looking for some kind of context, what context do I have? Query is what context do I look for? Key is what context do I have? So we will take a query of quickly, and it will look at the key of a run to see if key of run, if vector embedding run token has context that quickly needs. Now, if you are wondering, why do you need us to calculate a key to show what context token has? Why don't you just use token embedding to show which context token has? And I'm actually not sure. Maybe I will be able to explain in one of the next videos. But also, these embeddings are a lot longer than these key embeddings. So it would require a lot more computation. And also maybe this key is a bit specialized, a bit changed, and maybe it's showing better like what context it has, not just like the plain context like this vector would show, but like what kind of context you get if you take context from me. So if you have query for quickly and key for run, how do you find the similarity between that query and that key? And this is done with dot product. So these queries, you can look at them as coordinates in a coordinate system. So this is coordinate x, y, z. There can be like thousands of coordinates, which we wouldn't be able to imagine because that means thousands of dimensions. But let's take two vectors that have only two coordinates. So this vector, let's say this is the vector for the query, and this is the vector for the key that we are comparing. So we just, to find their similarity, we take a dot product, and I will show you how to calculate that product, but let's first understand what it means like intuitively. We draw a straight line to this vector, and the amount of overlap, this is the dot product. This will show the dot product, the length of this. So the length of this. So the more similar this vector is to this vector, then the length, this number length, will be higher. So that's how you find similarity by calculating the dot product. Let's say we calculate the dot product between query of quickly and key of ran, and we got some number. This is a pretty high number, 0.65. This means that ran is very relevant to this quickly, and it should take a lot of context from this token ran into this vector embedding to change this vector embedding. And if we were to calculate query of quickly with key of the, we will probably get a lot smaller value here, like 0.05, which means there isn't we shouldn't take a lot of context from this word the into quickly, because it's not relevant context and it will not help us. And if we were to take it, then it would just hurt the meaning of this. So it's not a relevant context and we shouldn't take so much of it, maybe just a little bit. So what converting to keys and queries does is, if you have these two tokens, these two vector embeddings that may not be similar, their vectors may not be similar, it's creating similar vectors, keys and queries, if the context should depend on each other. So first, we would usually take this whole matrix of all of the tokens, multiply with this matrix of queries, query matrix, and we would get a matrix of queries like this, and we will get matrix of keys by multiplying this all of the tokens with the key projection matrix. Once we have queries and keys calculated for each token, we still wouldn't go and calculate one by one, this guy times this guy. We would still use matrix multiplication to just multiply these two matrices, because it's more computationally efficient. But we can't multiply them like this. It wouldn't work because we need to multiply each query with each key. But if you know matrix multiplication, you know that this, if you multiply them like this, then this would multiply each query with this vector that's like first number of each key, which is not what we want. So if you don't get it, it's okay, I will explain. Here we have the same queries matrix. Here we have transposed keys matrix. So you can see that this is the first key, 0.21, 0.83, and 65. And now we swap rows and columns. So now this first key is actually like this, upside to up to down, 0.21, 0.83, and 65. And now the way matrices are multiplied, it's gonna work out. So the query, the first row, will be multiplied with the first column. So you can remind yourself how matrix multiplication works, but it will multiply the query with the key. And the way it will do that is it will say this first number times this first number in this column, second number in the row times second number in the column, and third number in the row times third number in the column, and then add up all of those three products. So you get a single number in the end. So this would be that single number here. So if you, I'm just explaining matrix multiplication now. So if you have this first row and first column, the result, this is same as dot product, by the way. So the result would be written at the intersection of this first column and first row, which is this number here. This number shows how similar this query and this key is. This query is, this is the query for the first token, whatever we had the first token. So here we have only 3 queries for 3 tokens to make it simpler. And this is the key for the first token. So it is calculating query of itself against the key of itself. Usually those things will be very similar, very high similarity. Okay, so then it would take like the query of the second word and check the key of the first word. So how much does the second word find the first word interesting, the context of the first word? Does it want to take a lot of context from the first word or not? If the second word is quickly and the first word is running, then it's very interesting, like it's saying that this quickly is referring to the word running. But if it's a different, less relevant word to the word quickly, then it wouldn't have such a very high dot product. So this matrix shows how much each word finds every other word interesting. If we have 3 words, then the first word will be calculated against itself and the other 2, the second also against all 3, and the third against all 3. Now I will replace some of the numbers here with 0. And I will explain why I'm replacing these particular numbers with 0. You should still ignore this apply softmax, what I wrote here. That doesn't come in yet. Let's see why I replace some of the numbers with 0. If we have the first query, the query of the first word, and the key of the second word, the problem there is the first word is checking what context next word has. But we know that LLMs, we don't know the next word. So during the training, we don't want to let the words look at the next words that come after them. So we just want to manually set this situation here at 0. So that means that the first word will take no context from the next second word. And here as well, the first word will not take any context from the third word. You can take pen and paper again and try to multiply, see how this is the third word, see how all of this makes sense, try to do it yourself. So we have the query for the first word and the key for the third word, but we don't want to allow that interaction. We don't want the first word to look at the third word because it comes after them. So we just set it to 0. Here we also don't want the second word to look at the third word at all because it comes after it. We only want to look for the previous words. Now it would be nice if each row added up to 1, because let's take a look at the third row. The third row shows for the third word, the third token, how much the first token contains relevant context for the third word, how much the second token contains of the relevant context that it should take, and how much itself. So this is, you can ignore this one. And it will be good that these add up to 1 for the third word, because so then we can say out of all of the context that we want to take, we will make like this is the highest number for the first word, so we will take like 55% of that new context should come from the first word, then a little bit less, 30% should come from the second word, and 15% should come from the third word for that new context. So this is how we will get a final vector that encodes not only the context of itself, but also the context of all of the words around it. And these three numbers show how relevant the first word is for that third word, how relevant second word context is, and how relevant this one is. So we will add in these amounts. How do we make this add up to 1? Let me delete this, then apply softmax. So instead, I just copied this guy and asked Grok to explain, and Grok actually made really good like numbers here that I can show you. This is the matrix that we start with. So we will perform some mathematics trickery, and for this trickery, we will need to set these zeros to -infinity, so our hack works. And let's ignore all of this, let's not look at that. So we will then exponentiate each of the numbers. So we will just put this number, e to this number, and e to this number, and e to this number. And when we put e to -infinity, we will get back our 0. So we want to keep 0 here. Whatever we do with these numbers, we want to keep 0. So the way we will keep 0 here, when we put something onto e, we just put -infinity onto e. I forgot to say though, our goal for this vector is to get number 1 here, because we want the vector to add up to 1, and we want to keep these zeros here. So the only way is we need to get number 1. Here we also want to keep this 0, but right now they don't add up to 1. So we want to keep the relative value of these numbers, or a difference of these numbers, same, but we just want to scale them down so they add up to 1. After we put each number to e, let's start with the first one. So the first one, e to 0.81, we will get 2.246. And we will just sum up the values of the entire row and divide each of the values with the sum of the entire row. And this is how we will keep everything add up to 1. So in the first row, we only have one number. And when we divide it by itself, it's gonna be 1. This is the first row. Second row, we have these two numbers. After we put them to the power, we put them e to this number, we get these two numbers. This is when we add this entire row. Can I zoom in? No, okay. And then we will just divide each number with the sum, and we will get a new row that has the same scaling, same difference between the numbers, but it just now they add up to 1. And same for the third row, sorry. So what we now have is we literally have a matrix that tells us when you are taking context, when you are expanding, let's look at the third row. When you are expanding context of the third vector, third token embedding, you should take 39%. 39% of that new expansion should come from the first token, and it's not this row, it's the tokens row, it's here. Let me show you. So let's say we have these 3, so 39% should come from this, and then 31.9% should come from the second, and 29.1% of the new expansion should come from the third row. Now we can come back to the value vector. You know, I was explaining what seems like long ago, query, key, and now values. Now that we have this matrix that says how interesting other context of other tokens is for each of the tokens, how much of the context each token should take from each other token, we will not use that to add directly these vectors. We will actually convert them, each of the vectors, to a new vector value. Imagine value as compressed vector of these vectors, and how it's different from query and key is, as I said, query says what I'm looking for, key says what I have for what you are looking for, and value says if you find me interesting, this is the information or context I will give you. So value is basically what context this token will give to the other vectors, other tokens. Now let's take a look at the third token. Let's say, for example, here we would look into this row, because this is the row for the third token, and we would see that third token finds context of the first token very interesting. So we will multiply the value of the first token with this number, and so this is basically interest number, and we would add that with another product, and the second product will be multiplying the value of the second token with this number. So this number shows how much third token finds second token interesting, the context of second token, and how much of the context it wants. And as I said, the context that second token gives to the third token is represented in the value vector. So we multiply the context of the second token with this number, and context of the third token, which is itself, with this number. And now we just add all those three vectors. So we add scaled value vector of the first, scaled value vector of the second, and the third into a new value vector. And now this new value vector will contain not only information that it previously had just about this token that it was created from, but this will also contain information from all of the tokens before it in certain amounts, context in certain amounts, depending on how interesting, how important those contexts are. And the importance of those contexts for this word was calculated with the Q and key matrix as I explained here. This is the calculation of how important each of the first, second, and third token is for the third token. I know this is all very confusing because there is a lot of logic and maths here. So I don't want you to get discouraged. It took me weeks and weeks and weeks to understand this. And this is all of I was writing so much in this notebook. A lot of the big part of this notebook is just me understanding this. So I would say, first, don't get discouraged, even if it takes you weeks to understand this. And I would really say that you should master this because, first of all, it's the most important mechanism of the transformers and modern AI, the attention mechanism. And what I'm going to explain next is just optimizations and improvements DeepSeek did to this. So you will need to understand this well to know how optimizations make sense. But before we continue, let's also make some intuitive sense about these projection matrices, because I did not explain them too much. I just said they convert token into query, into key, into value. So what do these numbers do intuitively? Let's first see what they do mathematically. So we have this vector. Let's just look at the first vector. Each of these numbers in the vector, as you already know, explains some of the features of the vector. So if this is, let's look at the vector dog because it's easier for me to explain. This could mean 0.5 that it's alive, or it's has like a lot of fur, or it's fast, or it's animal. So each of these numbers gives some attribute. If you increase the number, the attribute strength of the attribute would increase. So maybe if some attribute is explaining how much fur something has, for animals that have more fur, the number would be higher. Okay, let's now, so we know that when we are multiplying this vector with this matrix, we know that this vector will get multiplied with this column, so this row with this column, to produce this first number here. And then this row, same row, with the second column to produce the second number. That's how matrix multiplication works. So what does it do intuitively, this matrix? So you can imagine it as this. The first column will take the whole vector, whole token, and produce the first row, whatever the meaning of this first thing in the query is. So I'm pretty sure like this works like this. I'm 99% sure. So it would learn what's important. So this first column would learn what's important for the first number in the query vector to represent. And so it will convert to extract this information that the first number should contain. So the first column will extract information from the whole token that the first number should contain here. And the second column will take the whole vector and extract information that the second number needs. So each of these columns will learn what each of these positions in the vector, what kind of information they need. Now we will talk about some issues. Here we have 3 tokens, but let's say we have 100,000 tokens because context window, ChatGPT, and other LLMs is even above 100,000. For some it's 1 million or 2 million. So if we want to generate next token, we need to compute 1 million or 100,000 queries, 100,000 keys, 100,000 values. The solution there, actually, if you think about it, when we when we predict the next token, we can just add its query and key embeddings here. We don't need to recompute all of these because all of these are going to be the same, because as I said, the matrix that projects token to query is always same, and the token is always same. So the query will be always same for this token. So every time we create a new token, we just add one row and we store all of the other ones into memory. So we don't we gain compute efficiency, but we lose memory because we need to use more memory now. And also it turns out for each new token you add, you just need to store keys and values because you are comparing that new token against all of the previous tokens. So you need keys and values of all of the previous tokens. But you don't need queries for all of the previous tokens because you're done with queries. You just need a query for the new token, so you don't need to store queries into, just need to calculate the latest one. But this increased memory usage brings problems with it as well. For example, there would be just too much memory because it's also growing, but it's growing linearly now. It's not growing quadratically like before. The computation was growing quadratically. Now with memory it's growing linearly, but still it can grow a lot. So that's one problem. The other problem is within newest GPUs, they are calculating so fast that now moving data within the GPU becomes more of a becomes a bottleneck, not the speed of calculation. So now you don't want to have so much data and so much memory taken because now moving data is slower than the computation the GPU can do. So DeepSeek, first let me say that there are some techniques to reduce this memory usage, like grouped query attention, multi-query attention, but both of them reduce the quality, the accuracy of the LLM if you use them. But DeepSeek came up with a solution that reduces memory a lot and makes the LLM better, so increases the accuracy, which is crazy. So we will talk about that solution now. Now, if we go to this video, how DeepSeek rewrote the transformer MLA by Welch Labs, this screenshot is gonna help us understand DeepSeek's architecture a lot, and also this whole video will help you understand if you want to watch it. So here we have tokens. The American flag is red, white, and blue. And each token has 7,000 embeddings. So first, we will not directly convert these tokens into query keys values with matrices, as we were doing before. We will actually convert this matrix of these vector embeddings, so each token into some vector that is a compressed version of that token that contains information that we will later use to construct keys and values. The idea here is instead of computing whole key and value and storing it into memory, we will compute a lot smaller vector that will later help us compute key and values with computation for each as we are generating tokens. So we will just store this a lot smaller matrix into memory. If that didn't make too much sense, let's look at the formulas and it will maybe. So first we have vector embedding, HT. So if we go here, we have vector embedding. Let's say for the word red, vector embedding. Then we have a down key value. So this set of learned weights, so these are weights that network learns to like adjust their values, the ways that network learns, will convert this vector embedding into a latent representation that will later help us create keys and values from that. A lot smaller vector. So we are downscaling the big vector or the whole big matrix, downscaling it into just 500 dimensions. And then this 10 is 10 tokens. So for each token we have this one line of values. So before, like each vector for each token has 7,000 values, now it has just 500, and those 500 are representing like information necessary to create keys and values for this token. it says here, shared across all heads. Now, what are heads? I didn't talk about this at all. If we go back here, heads, you can imagine them very simply. We are calculating query key and value. What we do is we just separate, let's say this is a long vector, we separate this long vector into a bunch of like 8 smaller vectors. And we just pretend this smaller vector is query, the smaller vector is key, and the smaller vector is value, and then we make computations for those smaller vectors. And then the second set of smaller vectors, and then the third set of smaller vectors. And we do all of this that I was explaining, attention mechanism, but just with a broken and independent set of smaller vectors. So we just divide each of these vectors into parts, and we do computations independently. This is so each part can learn some other feature or characteristic that it's going to process. So the first head could learn about how to process if something is like a temperature of something. The second head could learn how to process like some other feature. So that's why we are dividing vectors into heads. I will show you here the same thing. We will just skip a little bit, but this is the key. This is the key vector that I was explaining for teeth token, so for the whatever the number of the token. And this, I think they just denoted that this key was made from this latent key query matrix. That's what this C means. So I wanted to show you that this long vector key is divided into heads, into parts. This is the first part. So you see it has exact same notation, number of token and stuff, just the number of head here, number of head. And then number of head, maximum number of heads is the number of the last head. So basically, as I explained, heads are just, you take the long token, you divide it, and then you just look each of these independently. So you look at this key head and this value head, and you process them and query. You will also have query head. The query head is here. Now there are two for some other reason. But anyways, yeah, you process them like they were separate tokens, separate things. This one and then this one, etc. So again, we look at this latent matrix. So each of these rows, the first row corresponds to the first token. And the first row says, holds information that shows how to create key and value for this token. And it's a lot smaller. It only has 576 numbers, while this token has 7,000 numbers. That's because the idea is that you don't need the full meaning of this token that this number holds. This number of like this whole vector. You just need like some information that is relevant to how to create a key and value. So you don't need all of the other information. So it says here, keys and values latents shared across all heads means this latent matrix is same across all heads. So it uses this for all heads. So this is stored in memory, it's a lot smaller. Now we do have some extra computation, but I think there are some mathematical tricks they use later to minimize this extra computation as well. But let's first see like what this extra computation is. So once we have this latent space, latent matrix for this token, for each computation, each next token we generate, we will look at this latent space and from the memory, and we will compute the key for this token. So this token, whatever it is. So we will use this matrix. This is the W up key. So this is converting the small matrix into bigger key matrix. So this small matrix, this bigger key matrix, it has more parameters. It will allow for more information to be encoded into it. It will be more helpful. So now the logic here seems to be, you have a very large token. You create a small matrix that says how to create a key. And if you remember, key says which information, which kind of context this token holds. So key is smaller than this token because key just explains what it holds. Doesn't hold all of the information, just explains what it holds. And it turns out the information necessary to create this key, this is getting a bit inceptive, but information necessary to create the key is smaller than the key. Yeah, it's a bit confusing. And of course, this matrix or this weight matrix and this weight matrix are just converting. So this is the down key value. Yeah, I should have said that this is for creating both key and value. So we're gonna use the same guy here to create the value. Yeah, this matrix is converting the big token into this guy, and then this matrix is upscaling, so converting the latent into this key. And you see here the key heads. So when we get the full key vector, we just divide it into heads, then process each head separately with the attention mechanism as I explained. We can see all of that here. So we have the latent space that we got by downscaling this guy, the token embeddings, and then we have W up K, which will convert this latent into the key matrix, and W up value, which will convert this into value matrix. If we go back, you can see that this same calculation happens here. The only difference is that we used a different set of different weights. So it's W up value. Here you can see this is it, W up value to convert this latent into this value matrix. Here you can see advantage. We are storing just this matrix into memory, which is 10 times 576. And this is same for all heads. So we are creating these two matrices, which are 10 times 128. It seems smaller, but remember, this is unique to a single head. So we create these two matrices for each of the heads. If we have 8 heads, let's say 10 heads, it's easier to calculate. 1,280 of these rows, columns, I don't know. Or we have like 50 heads, 100 heads, 128 heads. This can grow a lot actually. So we are not storing these big matrices for each head. We are just storing like this latent. That's same for the entire token, for every head in the token, for everything. Only thing we have left to explain is these two rows. Here we can see that, let's start from this row. So we can see for each of the heads, so this denotes key of this token, and I is the head, number of the head. So for each head, we concatenate the head that was produced by the C, by this compressed latent that I explained here, and this head that was produced with this rope. Now, what is this? So we are concatenating. So this holds information about the position in the sequence. So it says like you are the third word in the sequence from the, and the third verb from like beginning or from the some other word. So basically this just holds position information. This is rope positional encoding. So we concatenate this that just holds a semantic meaning, a lot of other meanings, but not the positional information, and then this head that holds positional information. And we do that for each head. Each head gets this positional information encoded. And you can see here, that this is same for each head. So each head gets this same guy, same. So it's the number of heads are changing. These are different heads, but each gets the same positional encoded head. Positional encoding is important because dog chasing a cat or cat chasing a dog, tokens are same, so these would be like same, but this now adds information about like the position of the token relative to other tokens. Now I will explain about queries, so if you understood the previous thing I explained, you will understand this easily as well. We start from the token embedding as always. And we have this down query matrix. This will convert this token into this latent query space thing that creates the query. So this is the small matrix that says how to create query for each head, and this is always the same across each head. Then you take this latent matrix, you multiply it with this up query matrix to convert this smaller latent matrix into this bigger query matrix. This is going to be one big query matrix or query vector. I'm pretty sure it's going to be a vector. So it's going to be a vector for this token. But it's going to be matrix when you add multiple tokens and you convert all of them together and stuff. So when you get this query vector for this token, you can then divide it into heads. Just separate into, chop up into heads as I explained earlier. And we also want to have positional encodings for each of these heads. So we will take the same latent vector and multiply it with this WQR, which stands for rope, I'm pretty sure. So we will just upscale this latent vector and apply relative positional embeddings, to encode like the position. Cat is chasing the dog, dog is chasing the cat. And we get a big vector that holds the relative, this positional encoding. And we split it into heads. And then we just concatenate the first head of query with the first query head that contains relative information like this. So for each of the heads, we create each of the query heads by concatenating the latent query and the relative encoding, positional encoding query. You will notice that before we had a same key positional encoding for every of the key heads, latent heads, that are created from this latent vector. But here we have each of the heads has its own positional head as well. And also only these two blue things are stored in memory. So the latent that can create queries and keys and values, and the positional rope embedding for the key. Scrolling down below, this is the exact same softmax operation that we had in the original attention that I explained 10-20 minutes before. So it's going to be the same, nothing changed. And as I explained in the end, what we do in the end, usually not just in DeepSeek but always, we have this value matrix and we have these attention scores. So we say since the cannot look at any future tokens, this has a number of 1, so the will take 100% of the value of the word the, and value of this token the is the first row here. So we just take the first row because that's the value of the word the. We multiply with 1 because it's taking 100% here. because there is nothing else to take from. And we just write the result as the first row here. So now the value is same as the value. So second row, American. As you can see, for word American, we will take a little bit of the meaning, because you see here the, and more of the meaning of American, because this is brighter. That's how I know it's more. That's how Welsh Labs represented it. Brighter colors mean like higher numbers. So maybe this is 0.2. So we take the first row that represents the, multiply with 0.2, take the second row here that represents American, multiply with 0.8, and then add up those two. And write a second row here, which means that because we multiplied the second row American with a lot bigger number, 0.8, then this final number result will have higher proportion of that number in it. And that's how we calculate this entire output matrix. So I can also show you just quickly for the last one. So the last one, blue, will take a little bit, actually a bit more attention from the, a bit less attention from American flag is a bit more, so this is a bit less. So we will take the last value, which represents the word the, multiply with, we will take the first value,
DeepSeek team point,
which represents the word the, multiply with this constant, the attention constant, plus second value multiply the second constant, third value multiply third, and then add up all of them and write them as the last value, last row here, last vector. And then finally, at last, you take each of these vectors, value vectors, that now contain context around them as well. They are 128 numbers long, but when you concatenate all of the heads, you concatenate them back, whatever the number of heads, now you will get a long vector. But this long vector will still be shorter than the original 7,000 dimension vector. So now, after everything, you will multiply this new value vector that contains context, long value vector, with a matrix, weights matrix that's learned during the training to convert this shorter vector into the original 7,168 long vector. So you just convert the value with context into the big vector, back to square one. But now this token, if you can, it's not a token, it's a vector embedding that has information of this token and the context around it. Look how many clips I recorded just explaining this multi-head latent attention. All of this. From 2 p.m. today until 7. Oh my, 5 hours just to explain multi-latent attention. So if it takes me 5 hours to explain it after I know it, then don't be disappointed if you cannot understand it in 5 hours. Now let's code it. We will code together and I will explain each piece of the code. DeepSeek has published really good code on GitHub, here in DeepSeek v3, and then inference and model.py. So this is code for inference, but it's almost the same for training, so we can start by coding this MLA class here. So let's go. I will create a new Python file, deepseek.py or model. It's actually not model, it's just deepseek.py. And the first line of code, class MLA, and this will inherit from NN module. Then I will just add some comment. Attributes that this class has are gonna be dimension. This is the dimension of the input vector. So this is just the token dimension. I can show it in Excalibur. So this is the length of the token dimension, token embedding vector. number of heads, as I was explaining, local heads. This is you are doing computation on different GPUs, so you want to spread heads onto GPUs. So if you have 128 heads and 8 GPUs, you would put 1/8 of those 108, 1/8 of those 128 into each GPU. Q LoRa rank. This is the size of let me go here. It's size of this vector. That's the latent representation that's necessary to create the query. As you can see, we have this token. This token has a dimension of dim, and this has the dimension of Q LoRa dimension, Q LoRa rank. Yeah, that's it. So it's a bit smaller, and this weight you will see later. So this will be a linear layer that will have input dimension equal to this dimension, which is dim, and output dimension equal to this dimension, which is LoRa rank. Then KV LoRa rank. So this, if I go back to KV, this is the rank of this latent representation that's necessary to create keys and values. And so this will be a linear layer that converts from the full vector embedding, token embedding vector length, takes that as input, and output dimension is going to be this KV LoRa, low rank adaptation LoRa, which is going to be this length. So you can look at this as vector, matrix, vector. Next one, QK nope head. So this means these are all of the heads that don't contain rope information. So you have a rope and nope. Rope contains positional rotary vector embeddings, and nope doesn't contain. So let me find, this is QK nope head dimension. It will be the length of these heads. So the length of this head. So this head is just a vector. So it will be length of this, and it will be length of this, which is, it will not be length of this. This is rope. So this is nope, no rope. And it's gonna be same query, query and key lengths, head lengths are gonna be the same. So you can multiply them. Multiply the query times transpose key. So you must have the same dimensions there. Let's go next. QK rope dimension head. So we're gonna have, so this is the rope dimension head. This is the rope head. This has certain length, and the same for query. Oh, I went too far. So in query, each head, rope head, is separate. So this is the length of the rope, one rope head. Then query key head dimension. So total we will get this by adding rope and nope head dimensions, because as you can see here, you get the query head by concatenating the latent one from the compressed and the one that has rope information, and same here, you're also concatenating. So the dimension of this head is nope plus rope. Value head dimension is just the dimension of this one head for value. Softmax scale in the code is defined as square root, so it's 1 over square root of the key query key head dimension. So this is it in the formula, and this is going to help stabilize. So some of these scores here, some of these scores in the attention can start to be really large. So if you have this row and one of them is a lot larger than others, then when you apply softmax, this guy that's very large will be close to 1 and all of the others will be close to 0. So then it would mess up, like you would add almost all of the value of that one, and so this square root of this helps stabilize, control the variance and stabilize the numbers so they are not so varied. Then let's write this init function, and it will get these arguments that are of type model args, and we will code this later, but I will show you now what it is. It just contains actual numbers for all of the arguments. For example, batch size, this is the number of sequences, number of independent sentences you want to process at once, sequence length. This is a big, so this is context window. I think this is maximum context window, etc. So we will just get all of these ones here into this init, and we will say super init to initialize the super class, so this NL module init. Let's go next. Here in the init, we will just assign all of these that I wrote in the comments. So this guy, number of heads, local heads is the world size is the number of GPUs you have. So local heads, as I explained before, is a number of heads per GPU. In the code there, they have world size at 1, so only 1 GPU. Let's go next. QLoRa rank is QLoRa rank. I explained what all of these means. Keep in mind, you see number of heads is always the same. So we have this big vector divided into heads, and there is n heads. So number of key heads, value heads, and query heads is always the same. Let's go next one. We just have these three that I already explained here. LoRa rank, we assign LoRa rank, KV LoRa rank. I think we don't. I shouldn't be repeating this maybe because you already know, or maybe we can repeat. KV LoRa rank is the rank of this vector, and then we have KV nope head, Q key nope head, Q key rope head. Let's go next. Q key head dimension, it's gonna be Q key nope head dimension plus rope head dimension. So you see here how you are concatenating those two, and same in the query. We just assign head dimension, the value head dimension here. Okay, where am I going? So then, if self LoRa rank is 0, so if we don't want to use these, like the thing that they just invented in this paper, the latent representations, then we will calculate weight. So we will define weight Q matrix, which is, it's gonna convert from the vector directly to this query. So this is how it works without like this latent multi-head latent attention that DeepSeek invented. If you don't want this part that DeepSeek invented, you just go from here to here directly. Then you have this query weight matrix, and we will use a column parallel linear. So for now, let's just imagine this is a linear layer, and we convert from self dimension, which is the dimension of this vector embedding of the token. That's input dimension. Output dimension is number of heads times the dimension for the query head, which is kept in this so we are computing weight for the query, right? Or we are defining it. So number of heads is, let's say, 128, and each of the heads has some dimension, 512. So the total dimension of this will be, when you multiply a number of heads and the dimension for each head. Of course, you will later split that into the number of heads, and each head will have that dimension. But for now, we are just converting the input token embedding into the query vector. Then else. So this is if we have LoRa rank. So if we want to use architecture of the DeepSeek. Oi, oi, oi. Before we continue, let me just explain this column parallel linear. This will act as same as linear layer if we have just one GPU. But if you have multiple GPUs, then while it's generating a vector, it's gonna split and generate part of that vector on each GPU. So here it would give this entire input vector to each GPU. And then on each GPU, it will generate just a part of this vector. So first GPU would generate first part, let's say 200 numbers long. Second part on second GPU, 200 second. And in the end, it will just concatenate all of those parts, and we will get 1000. If it's 5 parts, 200 numbers, so it's 1000 numbers long. We can check the code here. So I don't need to code this because it's very simple. You can just copy paste or code yourself with just a few lines of code. Linear layer with column parallelism, splitting output features across distributed process. So basically same as linear layer, but I will explain. So it gets in features, out features, same as linear layer. So in features is a dimension of this input layer, input vector. Out features is a dimension of this output vector. And out feature is not just the dimension, it's dimension actually here. So here it's dimension. Yeah, and this linear layer is gonna be this matrix that's gonna convert those input features into output features. So that's what we get, input features, output features. We don't use bias here, and data type can be some data type, but default is brain float 16 that I think I will talk about later, or you can search on YouTube. Then we initialize, and we initialize with all of those same arguments. So first we will check that number of output features is divisible by the number of GPUs, because we want to take calculation of this output and split it evenly across number of GPUs. So each GPU will calculate first part, then second GPU second part, etc. So it must be divisible here, and self part out features will be out features divided by world size with which will show the length of the number of features. So if we have 1005 GPUs, then this is 200 features that this guy needs to create, this GPU. And so we say super init, so we initialize a linear layer with super init, has in features, so it's gonna get the same vector, this whole vector, and part out features will get just the number of features divided by the number of GPUs, bias and d-type. And here forward is same as linear, so we just have linear layer. We have input x, which is going to be this token vector, self weight, so this is this guy that LLM learns during training, and self bias. We don't use that, and we get output y, which is going to be this one, and we return y. So this y would be just a part. If we have multiple GPUs, it would be just the part of this vector, or if we have just one GPU, then it would be this whole vector. And we also have this linear implementation. This is also what DeepSeek implemented. It's basically a linear layer, but it also has some handling of different quantizations and different data types that I will talk about later when we get to quantizations. Now we can continue, and this divided sign should not be here, but I'm not able to remove it right now because of my recording setup. So if we do have LoRa rank, we want to perform this latent, what DeepSeek invented. Then we will first start by defining this WQA matrix, which is going to be this matrix. So the reason they name it WQA is because this is the first part of generating queries. And so this is the first W matrix for the query. So this is this matrix. It's a down query matrix. And WQB will be this matrix later. As you remember, this matrix, down query matrix, will take entire token embedding and convert it to a latent space vector, latent vector for the query that shows how to create a query, holds information how to create query. So we are just defining this matrix here. It's gonna have this as input dimension and this as output dimension. So this is a vector and this is a vector. So it's gonna be a linear layer. Self dimension, this is the dimension of the tokens. Token embedding, vector embedding dimension. And self Q LoRa rank. As I explained, dimension of this small latent vector is the Q LoRa rank dimension. Next, we will normalize this output. So we will normalize this vector so the values are not too varied and weird, and it doesn't mess with our training, and we will use RMS norm. Here there is more explanation of how RMS norm is normalizing and stabilizing the values, so we don't get some exploding and vanishing gradients and stuff. Now let's continue. So we define the normalization layer or normalization step, and then we will define the second query matrix, WQB. This is this matrix that will take this latent vector that we produced in the first step and convert it into the query. So this is up query matrix. Up because it's converting a smaller vector into a bigger vector. That's why it's up. So we will also use column parallel linear. Self Q LoRa rank. So this is the rank of this guy. And we will convert that, upscale that into the rank of this guy, which is going to be number of heads times dimension per each head. So so this is query key head dimension. So the rank of this guy will be number of heads times dimension per each head. As I said, each head is a smaller vector. We will continue. So we say self WKVA. So this is the first part of the KV matrix. So we will go here, up here. This is it. This is the first part. This is down KV. So this will convert the input the vector embedding of this token into this latent vector that contains information on how to create key vector and value vector for this input token. So we are creating this matrix now. This matrix will have dimensions of input dimension is equal to this token, output dimension is equal to dimension of this, which is a lot smaller. If you remember, it was 7,000 here and like 500 here, the length of the vectors. And the height is 1 because it's just a one vector. So it's going to be linear. Input self dimension, as I explained, dimension of the input token. Output will be KV LoRa rank plus QK rope head dimension. Now, this is going to be a bit, they are now using some tricks to combine some of these operations into one. So it's more computationally efficient. here actually the output dimension is just this kv LoRa rank. So if we wanted to just calculate this vector from this input vector, we would just make this to have input of self dimension and output of kv LoRa rank. But they want to add in this calculation here as well, together with this calculation. So what they do is they have input same. So this is the input. But the output is going to be a big matrix or big vector. The first part of the vector, they will later split to be this LoRa, this latent representation. And the second part of the vector will be this rope embedding head for keys that has rope embedding information. I want to just show you what's going to happen later, what we will code later, so you have better understanding. So once we pass our vector, input vector, through this WKVA, which we just defined here, WKVA. After we get some output, which is going to be KV here, we will split that output into the KV. So this is maybe a bad annotation because this is actual KV. So this is the latent space. This is this latent space. And we will also get the key positional embedding. So the head, we will get this guy. But we will not exactly get this guy. This is the key that has positional embeddings. We will get something because this guy also contains, like, this guy is passed through the rope. So we will get something, some vector that's not yet passed through the rope. And after we pass that vector through the rope, we will then get this key that contains rope information. As you can see here, after they split the output by KV LoRa rank and QK rope head dimension into our latent vector and key with positional embedding, then they apply rotary embeddings to this key with positional embeddings, and then they get actual key with positional embeddings. I know it's confusing. I've been looking into this code for maybe 1-2 hours to really understand like what's happening, to be able to follow mentally. Long story short, we combined this multiplication and this multiplication here. So we just combine them like that. Let's go next. Then we will apply we will define normalization for just this guy. RMS norm and then KV LoRa rank, same as before. So then we will define the second part, which will be this this matrix, which will be converting this latent representation of the key value into this key vector. But I think we will use another trick here, but let's see. Column parallel linear again. So the input is KV LoRa rank. The input is the rank of this latent representation. The output is self.number of heads. So we need, say, so the dimension of this guy is number of heads times dimension per each head. So that's how you get the whole vector dimension. So number of heads times the dimension of the key head. But we will actually have a bit different here. We will have dimension of key head. So this is the nope dimension of key head plus dimension of value head. So here again, we are trying to combine this multiplication and this multiplication into one. I believe for computation efficiency. So we will just say the output needs to have, so the input is going to be just this, but the output needs to have this length, the first part of the output, and the second part of the output needs to have this length. And then we will just split the output into the key and into the value, and that's it. So you see here, the length of the output is number of heads times head dimension in the key and head dimension in the value. So we will get a very long vector and split into key and value later. Next, we have a row parallel linear. So we are defining the output in the end. If you remember, I explained in the end we are converting the value vector into the back to the full length token embedding vector length. Yeah. So we will say number of heads times value head dimension. So this is the value vector. And then the output is going to be just self dimension, which is the dimension of the token, the initial token vector. And before I explain row parallel linear, let me just show softmax scale. This is the square root of number of heads that we are dividing these attention weights here before we apply softmax. And this is going to happen way before this conversion of like to the output dimension stuff. This is going to happen inside of the calculating the attention scores. So let's explain row parallel linear. The column one was splitting output dimension across different GPUs, so each would generate part of the output. But here we are splitting input dimension across GPUs, and each GPU will generate the full output length. So let's say this vector is input vector. The first GPU will actually just get the first part of the input vector, input feature vector, yeah. And it will generate the whole length output. But this whole length output is just dependent on this first part of the input features vector. Second GPU will generate also the whole output, but it will just be generated from the second part of the input features. And so the third and fourth. And in the end, to make this output dependent on each of the parts of input features, we will just sum up outputs of all the GPUs. And with that sum, we made them all dependent. We made the final result dependent on each of the input parts. This will help us parallelize and distribute training. So we can just run all of these parts in parallel calculations instead of putting it all into one GPU and waiting for it to happen sequentially. Now let's take a look at this rope scaling. So first we will understand what rotational positional encoding is. If we have a sentence, dog is chasing the cat or cat is chasing the dog, it's important for us to know which word is where, the position of each word, relative position. So that decides the meaning of the sentence. So to encode the position, we will use rope, rotational positional encodings. Rope naturally captures the relative distance between tokens. So the order of words, the order of tokens is important, and also the distance, because if something appeared 100 pages before some word, usually, in most cases, it's not relevant or very little relevant to the current word. But the words around current word are usually a lot more relevant to the current word. So rope will encode the distance between the words. And rope will also allow that attention mechanism can still attend to a word that was 100 pages before. For example, if we have some murder mystery novel, in the end, where the crime is like uncovered who committed it, it's important to have attention to attend to some names or tokens like 100 pages before. So rope also allows us to do that. No additional parameters. Position information is encoded through mathematical rotations, not learned embeddings. So we don't have additional numbers and parameters to train the neural network for. So no additional computation to train these parameters. And the third one, rope allows models to handle longer sequences that they were trained on. I'm listing advantages of rope before I explain how rope works. So this is it. We are extending. So if we are using context for this transformer that's longer than what DeepSeek, this transformer, was trained on, the learned weights, then we will use this to extend the context window, which is allowed by rope. And it will not mess everything up, because in the 2017, the original transformer, if you extend the context window before after what it's trained on, then the perplexity of the model gets so high and it just spits random stuff and doesn't know what to talk about, like doesn't know which tokens to produce. Let's say we have some vector that represents the word cat. This is the token, this is token embedding. So it's only two numbers long, 2 dimensions long, so we can draw this on this coordinate system. And I'm gonna say that d is equal to 2. So this is the number of dimensions. Now, if this cat is the first word in the sentence, in the sequence, in the context window, then this parameter m will be, m will be 0. If this cat comes at second place in the context window, then 1, then 3, then 4. So we have this number m that denotes which position in the context window this token embedding is. And what we will do, depending on this position, we will take this vector and rotate it by a fixed angle. Angle of rotation is same, but rotate it number of times. Number of times depending on which position it is in the sequence. So we will rotate it 3 times by this angle that was maybe, these angles are very small, 0.0001 degree or something like that. But I made a very big here to show you better. So it will be like this. So this is how positional encodings work. And you can imagine that we have some other word in the context window. Now what's gonna happen is, the further apart these words are, the further they will be apart when they rotate. So if the dot product of them is similar, the meaning depends on each other. If they are further apart in the context window, then the meaning may not depend so much on each other. The further apart they are, the less they are correlated. So the semantic similarity between them, maybe they shouldn't attend to each other. So if we don't want them to attend each other if they are very far away, then the further they are, the more we rotate both of them. So for example, let's say this guy is in the beginning, so he just rotates like a few times, and this one is like 1,000 tokens away, so it rotates a lot. So now they are, when you dot product them, they will have a lot smaller dot product, like just here a little bit. So they will not attend to each other so much. Now what happens if they are so far away that they start circling around and now they are close? So even though we don't want them to have high dot product because they are like so far away, now because of this rotation they're gonna get closer. This is why we do another thing. We have another variable I, So in reality, this vector embedding will be a lot longer than just 2 numbers. So here I made it 6 numbers. And here is what we do. Here is how we can make sure that even as it rotates, the LLM still knows which one is far apart, even if one of these comes close. So we will define them in pairs of 2. So these 2, and then these 2, and then these 2. And for each one, we will have this rotation vector. So if we look at this cat, okay, so what I will do is I will delete this guy for now. So we look at the cat. The first pair is this. The second pair of coordinates, whatever it is, like these are just random coordinates. So we can draw some random vectors and everywhere. But the thing is, we will do the following. We will rotate the first 2. You see here, lower dimensions pairs rotate slowly, capturing long-range patterns. So these first 2 dimensions, we will, let's say this is the vector for the first 2 dimensions of the word cat. We will rotate it only a little bit, only is by 0.00001. So if we have another word, and I will color this white because this is for example dog, first 2 dimensions of the word dog. And so this is rotating so slowly that no matter how far apart these are, it will never like circle around. It will always just keep rotating a little bit more. That's why we put a really low angle, really small angle of rotation here. So the first 2 dimensions, the AI will look into it, look at the rotation, and it will know that if it goes here, then it's really far away. And there will not be any circling around, so it will just look at this distance. I equals 0 means we are looking at the vector for this denotes vector for the first pair. If I set I equals 2, now we will look at the vector for the third pair, because index is 2, it's a third pair. Now let's see what other dimensions encode. As I said, so this is let's say token dog, the first one. So as this one rotates, the attention mechanism will know how far away, like if this rotates this much, it knows it's very far away. But if it rotates just this much, it knows it's close around here. But to be more granular, like where exactly, because a small rotation here can still show hundreds of tokens distance. So how do we know exactly which token? We will use another pair that's going to rotate a lot quicker. And so each of these pairs will rotate at some rate. But beginning pairs in the beginning rotate a lot slower, so they will show the long distance. Like if they are rotated much, that means the distance is huge. But the ending pairs, the higher dimensions, will rotate a lot quicker. So, and they are able, so if they are like here, then they show, well, the distance, long distance is not that big, but so it's somewhere in the proximity, but where exactly? Well, how much is this rotated? If it's rotated like this, maybe 1 token away, 2 tokens away, 3 tokens away, 4 tokens away, 5 tokens away, but it does start circling around. So you don't know exactly if it's here, like, what does it mean? Like, is this like 2 tokens away or 7 tokens away, because it's circling around. But that's why you have a lot of these vectors, a lot of these pairs. So if the vector is 7,000 numbers long, then you have 3,500 pairs. And neural network will just look at all of them. So it will look at this one. Okay, it's not that maybe far away, or it's not that far away. And then it's gonna look at this one. Now this may be like 2 places away or 7 places away. It's gonna look at this one. So this one will maybe rotate like slower. So this one will show that, wait, if this guy is here, that means it's like further away. So maybe this one is 7 places away. So from this configuration, it figures out that this dog token is 7 positions away in the context window. So I'm still trying to figure out, because explaining is this is a skill in itself. So I hope maybe that my explaining of rope and stuff improves. You can watch maybe the next video I release. I will explain it better or have better graphics. So I hope my explaining skill also improves with videos. Now I will explain this new piece of code that I added. This guy will extend context window of the model after it's been trained. So if it's been trained to have a context window of 100,000 tokens, we can extend it to 200,000, for example. And I will explain how. Let's go back to our drawing board. So if we just naively put 200,000 tokens, it's not going to work, because this, for example, this guy that rotates very slowly, it's gonna rotate so far away, and the model has never seen it rotate this far away. So it will get confused, and perplexity will go high and everything. So we cannot rotate this guy more than what model has seen in the training. So the way we solve this is, if we have 2x larger context window, then we rotate these guys 2x slower. So now we can fit 200,000 tokens into, for example, this range, because we rotate 2x slower. Whereas before we were rotating 2x faster, so we only fit 100,000 tokens into this range. Now there is a problem with that as well. Because I'm rotating slower, let's take this one for example. I'm rotating slower, I rotate less, so the dot product between this one, the dog and the cat positions is gonna be higher, and we don't want that. We don't want to affect the dot product. So now the AI would think like this is more related, more similar, which we don't want to happen. We want to have the dot product remain the same, while this is just rotating slower. When we scale the rope frequencies by dividing by rope factor, so rope factor here, you can see it here. Token positions rotate more slowly with distance, so the rotation is slower. We know that. This means dot products between query and key vectors decrease more slowly with distance. The raw attention scores become more similar across different distances. As I said, the vectors are now have higher dot product. And because those raw attention scores become more similar across different distances, this would naturally lead to a more uniform attention distribution. So now we go from a more confident peaked attention distribution to more uniform, like peaks are lower and these valleys are higher, so they are more uniform. So we want to return them back to being peaked and low. To counteract this and maintain similar attention patterns to the original model, we need to increase the softmax scale. This is exactly what the code does. So I will first explain what this softmax scale does. This softmax scale is literally the opposite of temperature. When you go to OpenAI's API, you have temperature. So basically, if you decrease the temperature, you get more deterministic tokens results. So it's good for mathematics. And you want to increase temperature if you are doing creative writing. So the tokens are a bit more random or creative. But softmax does the same thing, but it just works the other way, where you increased softmax scale to have more deterministic, while you were decreasing temperature to have more deterministic. And if you reduce softmax scale, you will get more random numbers. So this is how it works. Let's say we have some vector 2, 1, 0. We apply softmax, so they all add up to 1, so we will get the 0.67, 24, and 0.09. Now, if we want to make these things more peaky, so we want to increase this number while decreasing this number and maybe keeping this number in the middle or a bit lower, we would do that if we want to For example, in terms of producing tokens, we want to maybe increase the most likely ones to even higher so they get chosen. So this is good for mathematics where there is only one correct result. So we want to pick the ones that are most confident. So here we would multiply with 2. This is the softmax scale factor. So we would get 4 to 0. After applying softmax, we see that this guy peaked a lot, and then these two reduced. So now this one is more confident. Now, as I said, softmax scale is opposite on temperature because we are increasing softmax scale to increase peakiness. And in temperature, we are decreasing temperature to increase peakiness. So as I said, because of the slower rotation, the dot products are more similar now. So they are more uniform. We want to return them back to being less uniform and more peaky and have more valleys and stuff. So we will just apply this softmax scaling to make them less uniform now. The balance is critical. Scaling the rope frequencies too much without adjusting softmax scale, attention becomes too diffuse and uniform and all of the attention scores become similar to each other. Increasing softmax scale too much, attention becomes too concentrated on top scoring tokens. So when we increase the distance, then top scoring tokens will have very high attention, which is not good either. Then it will only select those tokens. Just right, the model's attention behavior at longer distances, I would say at all distances, mimics its original behavior at shorter. I'm not sure what they mean here, but it mimics, yeah, maybe what they mean, like, I don't know what they mean. I don't know what they mean. So we just use these two to balance each other. I want to first know, why are we applying logarithm function to row factor? Okay, let's consider two tokens at position 0 and 8. In the original model, where row factor is 1, where we are not scaling a context window, position 0, no rotation, position 8, rotated by 8 theta. Their dot product might be something like 0.5, decreased due to positional distance. So maybe the dot product of the meanings of these two tokens is 0.53, but because there is some distance, it's decreased to 0.5, because they are not so dependent, because they are more distant. Example 1, rope factor is 2. Now we extend the context window by 2x. The rotation angle becomes theta over 2 instead of theta. Now it's rotating 2x with 2x smaller angle. The position 8 is now rotated by 8 times theta over 2, which is 4 theta. This is equivalent to position 4 in the original model. So now model sees this as token as like being on position 4. Effect on attention scores. Position 8 now looks like position 4 to the model. The dot product increases from 0.5 to 0.7. So I think it wouldn't be this much of an increase. Maybe from 0.5 to 0.55. So now this is not good because now we are rotating slower and this is causing the dot products to be higher. So we don't want to see this increase in dot products. Okay, here, let's take a look at this. We see rope factor going from 1 to 4, 8. So we are 2xing context window, 4xing context window. And we can see difference in attention scores as this happens. So the original attention score, 0.5. Now that there is less rotation, then the attention score will be a bit bigger, higher. And then less rotation, higher attention scores, less rotation, higher attention scores. But as row factor doubles every time, the difference in scores does not like become 2x double smaller, or it's increasing with diminishing returns. So first it's increasing by 0.1, then by 0.07, then by 0.02. So even though this is scaling multiplicatively, this is just scaling either linearly, because I'm not sure like if it's scaling like this, maybe linearly or a bit differently, but the point is it's not scaling as fast as this. It's not doubling every time or something. This is because if you make the distance double, like the distance between vectors 2x smaller, then there will be significant increase in the attention score. But then if you make that 2x smaller, then this closing up is not as huge as this closing up. So it will not have this huge impact on the attention score. And then if you make this distance 2x smaller by extending the context window by 2x, then it will have even smaller impact on the attention score, because the vector moved just a little bit more. So we want to somehow implement this relation in the formula. And it's right here. You take logarithm of rope factor when you are applying a rope factor to scale the softmax scores. So you take logarithm. So this means as you increase this, as you keep doubling this, the more this increases, the more diminishing returns you will get from it, because logarithm will just clamp or reduce huge values. And the bigger the value, the more it will be reduced by the logarithm. Then in this formula of m scale, we also have this args m scale. So this is a hyperparameter that you choose when defining the model. So here, values around 1 are a good starting point. Lower values, less than 1, make attention more diffuse, so it makes everything more similar. And higher values make attention more focused or sharper. So we would choose higher values here because we want to sharpen the attention, because they get diffused with the changing in the context window. I forgot to say, sorry, m scale, this variable m scale determines how much you are going to scale the softmax. So if you are scaling the context window a lot, then you want to also scale the softmax with m scale to be more peaky. To calculate m scale, and this happens, I don't know if I explained this but if max sequence length is greater than the original sequence length, so if we scaled the context window, then we want to increase the softmax scaling as well with the m scale squared. Why exactly m scale squared? I guess somebody just figured out it works well, but to be honest, this is confusing for me as well, because squaring it means like the higher it is, the more effect you want it to have. But the only variable that we have here, row factor, and we are putting it through logarithm, means the higher it is, the more we are reducing it and constraining it. So I'm not sure if this will actually reduce the high values and make them less effective, or it will explode high values. So let me recap. Here we have this m scale. We have +1, meaning that whatever number we get here, it's going to be over 1, which means that when we are squaring it, it will make attentions more peaky. So we are calculating how much over 1. And we have this rope factor, which is the factor of scaling our context window. So as I explained, the more you scale context window, the less effect it has on, the less change there will be on the softmax scores. So if you scale the context window a lot, you don't want it to have to contribute a lot to this formula, because you want to clamp it down with the logarithm function. And we have this manually determined parameter that's For DeepSeek, just set at 1, so they will just keep it, not change anything. And just scale down this whole expression with 0.1, so it doesn't have a strong effect. So here we would get something like, I don't know, maybe 1.2 or something. And then we scale the softmax scale with 1.2 squared. Let's now encode KV cache. So we will use this to store cache for each token, so keys and values into cache, so we don't need to recompute on every next token, as I explained in this video. If attention implementation is naive, so if we are not using DeepSeek's attention implementation, but we are using the 2017 attention implementation. Then self-register buffer, so this will create a tensor, but this tensor will not be used in the neural network. It will not be learned or changed during the training. This is just a tensor that holds some values. We will call it kcache, key cache. Initialize with torch zeros, and the size dimensions will be batch size, so max batch size. So this is so I will explain first sequence length. Sequence length is the context window. So whatever, if it's a one sentence, then that's the sequence length, sequence on tokens. And batch size is how many context windows do you have. So you will, for example, train on each separately, or I think this batch size is used if you have multiple different conversations. For example, during inference, if multiple users are using conversation, talking to the AI, then you have this batch size, each storing separate conversation, which that is separate sequence length. But I might be wrong on this. Number of local heads. So number of local heads and head dimension means like you will. So when you multiply these two, heads times head dimension, you get the length of the key. We can check it here. Key. Yeah, here. No. Yeah, here. All of the heads, and each of these heads has its some dimension. And then persistent false. So we don't want to store this into memory. We just want this during runtime, as person is conversing or as we are training. Next one, we will do the exact same thing, but for value cache. Everything is same. It just the difference is here. In value head dimension, this is QK head dimension. But if the implementation is, if the implementation is DeepSeek's implementation, then we will, instead of storing the full array of keys and values, we will just store this latent vector that helps us create keys and values, this small vector, and this key head that contains, or this key vector that contains positional rope encoding. I will explain, don't worry. So I will show you here. So everything is exactly the same. Here, KV cache. So this is this KV cache, what we are talking about, this matrix. So initialize with zeros, batch size, max sequence length, this is the same. But here, instead of having a number of heads times head dimension, we just have LoRa rank, because this is same across all heads. So we don't need to have separate vectors for separate heads. This is the same, so we just need one. So that's why we don't have this number of heads. We just have the dimension. And the dimension here, the LoRa dimension, is a lot smaller than this full head dimension. The full head dimension is still gonna be like present here later when we calculate it, but not in the memory. In the memory, we are just storing the small matrix. Then continue. We will do the same for this positional encoding cache. So this is gonna represent this blue guy. This is the same for each head. So this is just a small vector, or it may not be small. This is a vector that contains positional encoding for this token that will be concatenated to every head of the token, of the key of the token, later. And it's always the same for every head. So everything is same, and here we still don't have number of heads because it's same for every head. We just have the rope head dimension, and the dimension is same for, so we use this variable for query key rope head dimension. Now we can start with the forward function. It's gonna take some parameters, and I will explain each here in the comment. Arguments: x storage tensor, input tensor of shared batch size, sequence length, and dimension. So this is an array of embedding tokens. So we have this sequence length is context window. Each context window has tokens, and each token is represented with a vector. So sequence length dimension, and batch size is how many conversations in parallel. Starting position of the in the sequence for caching. The sequence will have, each token will have keys and values. So this start position will show at which position in the KV cache we will store the key for the first token, and then the next position will store key for the second token, etc. But we will look into this deeper when we get to this later, so if you didn't understand, it's okay. Here, frequencies, so pre-computed complex exponential values for rotary embeddings. So you know that I explained in rotary embeddings, each of the tokens, each of the vectors, keys, and queries have some rotations. So these rotations only depend on the position in the context window, and they depend on the position of the number pair in the vector for the key and query. So what I'm trying to say is they don't depend on the key and the query, they just depend on the positions. So we can pre-compute them for each position. So we can just pass them here. We don't need to compute them with every token. Then mask, this is masking future tokens. So whenever one token is attending with the query and checking the keys of other tokens, we don't want it to check the keys of future tokens, just the previous tokens. Returns output tensor with the same shape as input. The input is going to be batch size, sequence length, and dimension of the token embedding, and the output will be same shape. So it will, I guess it will return whole batch size and sequence length, but everything will be unchanged except the tokens. The tokens will be juiced up with the context around them, with the context of the rest of the sequence. First, we will extract batch size and sequence length, because we will use them later to reshape a tensor. So we just need these like dimensions. So then we will calculate end position. So if you are generating 20 or 100 tokens, your start, and you have like 100 tokens in the context window, then your start position would be 99, because first tokens in the cache has index 0, and the 100th token has index 99. So now you want to generate 100 more tokens, so the starting position is going to be 100 now, because that's where you will store the next token when you generate it, and then the next token after that, starting position in the cache is 101, etc. But we want to find end position. It's going to be start position. So start position where you start generating in the context window, plus sequence length. Sequence length is going to be the maximum length that you will have after you generate the new tokens. If self q LoRa rank is 0, So if we are using standard attention, not this multi-head latent attention, then query vector will just be passed through this linear layer WQ matrix that we defined up here. This is a standard calculation. Else, if we are using DeepSeek's implementation, that we will do it a bit differently. First, we will pass the input, which is a batch size sequence length dimension. So this is these tokens through the first part of the equation. So that's going to be this part to get this. Then we will normalize it. So we will normalize this to have stability in the numbers and training. And then we'll pass it through the second part, WQB. And the second part, WQB, that's gonna be, sorry, we are calculating queries here. So the first part will get this, and the second part is this is the WQB matrix, and we will get the full query vector. Next, we want to transform this vector. So we will keep batch size sequence length same, but we will now have this, we will separate the last. So I'll show you here. We have one long vector and we need to separate it into different heads. So we will have two new dimensions instead of the last dimension. So it will be number of heads and then length of each head. So number of local heads and head dimension. So that's how we made this vector. Then we want to separate the heads of query that don't have positional encoding and ones that do. Because if you remember in our code implementation up here, we did this trick to increase the speed of computation by combining this calculation and this calculation. So now they are combined and we want to separate them. So now each of the heads contains both one that does not contain information about position and ones that should contain, but we did not apply positional information to this part, these heads that should have them. So we need to separate them and then apply rope and then concatenate them back. Torch split. So yeah, we are splitting the Q vector and we are gonna split into nope head dimension and rope head dimension alongside the last axis, the innermost axis. And so we have Q positional head. We will apply rotary embeddings and pass in this vector that we split here and these frequencies that I explained before. This is the input variable here. So this is also a custom written function. We will leave it at that for now. So now we will get the key and values. So we are calculating this latent key value matrix by putting it through this this linear matrix weights and then so we will now split what we will split is we in the code implementation, I explained it in the video, we combined this calculation and this calculation. So now we will split this result from the result from this calculation, and then the result we get from we split that's for this calculation, we will apply rope to it to get this guy. So the way we will split is torch split KV. It's gonna be KV LoRa rank, so this is dimension of this one, this vector. and this is the dimension of the rope head dimension vector. So that this is this vector. And the dimension is last dimension. So now that we have this part, the head positional encodings, we will pass that through applying rotary embeddings. We will implement this function later, but what it does is it takes this because this function requires a certain shape, and we need to expand this by one dimension because this key positional encoding head doesn't have head dimension at all. Because if you remember, it's calculated directly from this input, and this matrix does not have a head dimension. It just has like the length. So this doesn't have any heads. Same for every head. This is also same for every head, so it doesn't have head dimension. That's why we need to add this head dimension. That's gonna be just one like length. Continue. If we have naive attention, then we will, to create a Q vector, we will concatenate the Q nope head and Q positional encoded head. Here in the Q, we are concatenating nope head and rope head. This is along the last dimension, because the dimension here is batch sequence length and number of heads and head dimension. Then for KV, we will just pass this through, so first through normalization. So we are passing this guy through normalization. No, this is Q. So this guy through normalization. And then we are using this matrix. So that's going to be this upscale. So we convert this latent space of KV into KV. Due to our shortcut hack, we are going to, we combined this multiplication and this multiplication. So we combined this matrix and this matrix. So we will get, each head will contain the key and the value. No, there is no heads. We will just get the key and the value concatenated as a big vector for each token. And now we need to split the key and the value, and then split each into heads. Let's go. KV is equal to KV view. So now we are splitting key and value. No. Wait, what are we splitting? Yeah, we are splitting key and value. So we have number of local heads. And now, so we are now splitting heads. So we are doing this operation first. So now we will just get a bunch of heads, and each head will contain this key and this value concatenated. So we are doing that step first splitting into heads. And each, okay. And then we will split into heads. So we will separate value heads and key heads. Torch split, KV, self key nope head dimension and V head value head dimension along last dimension. Now we have it separated like this, each head for key and each head for value. What is a little bit confusing, actually nothing is confusing, I think. Yeah, okay. Next, we want to append this head that contains rotation position information to each of these heads. So first we will need to expand the dimension of this so it matches the dimension, and then we will just append here to everyone. So let's see how we do it. K is equal to torch concatenate. So we have nope heads and this head, and we need to expand it 0 0 -1 -1, sorry. So this is going to be batch and sequence and number of local heads. So for each head we will have one of these, and it will just be one within each head. alongside the last dimension. Then we will store the key into the cache from starting position to end position. So just continue wherever this sequence of tokens left off. We will generate new tokens, store the keys for each token. Same for value. Okay, then we will calculate these scores, attention scores. We will use einsam. So we are going to multiply queries with keys, but we will not look at the keys, at the words after in the future, as I explained this in the beginning of the video. So this is the classic attention here, the attention formula. Queries times keys transposed, because we are transposing it here. We are defining this transpose here. And once we calculate that, we will get the attention matrix that I explained. I have it in my video. And then just softmax, apply this softmax scale. So that's gonna be square root of dimension heads. Or if we have a different softmax scale, if we are scaling, then it's gonna be different. Then we have else. If it's not naive implementation, if we are using DeepSeek's implementation, we will do the following. We will assign, so we already have this, but we need to see if we need to dequantize these weights. So it will be, the weights will remain the same if the scale is none. So if we don't use any quantization, and I will talk about quantization later. Else, weight dequantize, and then we will just pass in the parameters to this function that we will define. So weights, scale, and block size. Then we continue working on this vector. We need to transform its shape. And the transformation is going to be of shape n local heads -1 to fill any dimension here, and kv LoRa rank. So this WKV matrix, before we change its view, this is what this is the shape it has. So the input shape is kv LoRa rank. So this is this matrix. So we are gonna combine this matrix and this matrix. So the input is kv LoRa rank, and now we will define these two. So the output should be key vector and value vector. So it's number of heads times key head dimension, and it's number of value heads times value head dimension. This is the output. So number of heads, which is same for key and value, keys and values. And so key dimension of the head plus value head dimension. So that's the output. So here we input the small vector that contains latent representation to create key and value, and we output two concatenated vectors, which is big key vector and value vector. Then they perform a bit more mathematical trickery to eliminate some computations. So here you can see that we are multiplying this latent vector with a matrix that will produce the key vector. And we are doing the same for the query. Latent query times matrix that will produce the query. So we have one calculation, two calculations, and to get the scores, we will multiply the resulting key with the resulting query. So that's the third calculation. So they can actually perform some tricks to turn 3 calculations into 2 calculations. So they will first take this matrix that converts into the key, and they will just add it multiply these two with that matrix. So they will add a third matrix here. And so when they multiply the query, they will also multiply this with this matrix that transforms the key, and they will transpose that matrix, because you remember that we are multiplying query times key transposed. So that's one calculation, the 3 factors. And then whatever they get, they just multiply that with this latent that will produce the key. So that's the second calculation. And then that will yield the score. They also absorb this upscale value weights. So instead of calculating value here from the latent representation, they absorb this into the final output. So this output is converting whatever the last value is into the full token embedding size. So when everything attention layer is finished. So they add that here, multiply this and add this W up value matrix. So guys, I have explanation here to the side. This part is a little bit tough for me to understand, like all of the matrix multiplications, because I'll show you. I'll paste all of the code, and I will explain all of the code, all of the whole chunk. But as you can see, there is a lot of sum multiplications, and I'll try my best to understand what all of this does, but I don't get 100% all of the sum transformations and multiplications. But we can try anyways. Hopefully by the time they release DeepSeek R2 or something and I make a video, then I will have more time by then to understand all of this stuff. So we left off here. This is transforming or merging the up key weights into the Q weights. So up Q weights, projection and Q projection weights. Then we are saving normalized key value, this matrix, into cache. And we are also saving the positional, this into cache, the key positional. So, and I believe unsqueeze 2 is because they're going to concatenate these to these, so they need to match the dimension of the positional encoding embedded head. So you see here, this is just one vector, but here, this vector is divided into a bunch of vectors. So each vector, so this long vector has smaller head vectors. So you need to add one dimension around here, because then this vector will get matched to each head. And then this is just calculating the scores. So I was confused here because it says it's using this KV cache to calculate scores like this. But my understanding was that it should convert that first to keys and then calculate scores with that. But as I said before, we merged this conversion matrix into the queries. So now we just need this latent vector. We don't need to, yeah, so we don't need to calculate keys. We can skip that. So here, this guy has, so that's the formula here. And also there is this conversion matrix in that as well. And then KV cache, it's just this. And in the second one, there is no merging between weights. We just calculate the query with positional embeddings with the key positional embeddings head. So just this guy with positional embeddings with this guy. So that will be this part of the query vector with this part of the key vector, because they are concatenated. Then we add up those two calculations and we multiply by softmax scale. We use softmax scale for any of the reasons. For example, if we are scaling the context window, as I explained earlier, we are applying rope extension, then we need to increase the softmax scale. You can skip back to the part of the video where I explained this. And after that, if we want to apply mask, which we want in LLMs, then we will just mask out so that no query can interact with the key of future tokens. So no query can look at the future tokens. That's the mask. And in the end, after we have, so did I say that we apply softmax? I think I didn't say that. And after that, we have attention matrix. And then we, as I explained in the beginning of the video, we will just do that. We will apply attention to each value and add them up. As I explained, you can always check the timestamps below to figure this out, but we are here applying scores to values. And so this is if the implementation is the 2017 implementation. But if we are using DeepSeek implementation, then, as I said before, we just need to multiply scores and values. Now this is KV cache, so this is not this value component that we are supposed to multiply with. This is this component, and so we will just multiply with this in this step, and in the next step we will apply. So that's this component, same as this. We will apply this conversion upscaling value. This is to reduce computation. So this is, we are merging this upscale value matrix into this computation, so to reduce number of computations. So that would be as if we multiplied it here and got value, and then multiplied value with attention scores. So here we are doing einsum. This is the output, and we need to apply this upscale value matrix multiplication onto this output to get the real output. So in the end, this WO, this is projecting our juiced up value vector that has all of the context around into a big token embedding, same size as token embedding. Now this new token embedding basically has all of the context from other tokens around before. So what we did, what this X is, it's same shape as the input, which was batch size, sequence length. So sequence length is context window, and batch size means like you have multiple independent conversations, and each conversation's sequence length has a number of tokens. And each token has a dimension, vector embedding dimension. So we will get this same output as input to this forward function, but this vector, token embedding, will be like juiced up with context from other tokens that come before it. Finally, we finished MLA, multi-head latent attention. It was tough. It took me 1.5 days just to explain it. So if it takes you, like, if you can't understand it in 1.5 days, don't be disappointed, because it took me that time to just explain it. Let's take a look at the second step. So we talked about attention, RMS norm. Now let's talk about feed-forward network, which is DeepSeek mixture of experts. In mixture of experts, we are at this point, this is what the self-attention mechanism, multi-head attention, gives us. After that, we give this vector embedding. So this is vector embedding that has contextual information from other tokens around. We give that thing into the feed-forward network. And the feed-forward network will process it in some way and give processed version of that vector embedding. So when we get this token from self-attention mechanism, we just added a bunch of context from other things. Now we want that context to be processed, refined. So what feed-forward network is going to do, it's going to identify complex patterns in the contextualized embeddings, filter and emphasize important features, suppress irrelevant information. So it will process. You can look at the self-attention as discovering and adding or mashing all information, context, and then feed-forward network making sense of all of that additional context from other tokens and processing it. In essence, if self-attention is about looking at all other tokens to understand context, the feed-forward network is about deeply processing what the context means for each individual token. So how does a DeepSeek mixture of experts work? Here we have this input embedding, and we have shared experts and routed or selected experts. Each of these experts that you see here, each of these squares, is a neural network, and it specializes in one thing, or not one thing, it specializes in certain things. So there are maybe 128, for example, different experts, different neural networks, and depending on which embedding you have here, the model will choose experts that are most suitable for that embedding. So if we are solving mathematical task, we will choose, or model will choose experts that's best at solving mathematical tasks. Here you can see that we have some shared experts. So shared experts are always chosen. So model pushes the embedding through shared experts always, and chooses some selected experts as well, depending on the task. The idea is that shared experts are gonna learn some kind of knowledge that is always necessary to process language for every, no matter if it's mathematics, language, whatever, mathematics, history, whatever. So that other experts don't need to learn redundant knowledge. So if there was no shared experts, then this knowledge would have to be learned by multiple other experts, because every time you process a token, that knowledge would have to be present. And if there is no shared experts, then every expert or a lot of experts would need to learn that same knowledge because it's necessary always. So we have shared experts for shared knowledge, and then we have selected or routed experts that get selected based on the current task, the context of the embedding. So the choice is made with a scoring function. They call this mechanism gating function. It will assign score to each expert of how relevant this expert is to the task. For example, if we have mathematical task, mathematical experts would get maybe high relevance, maybe 0.5, while less relevant experts would get 0.05 or something. And then we choose top k. So this k is some constant, maybe number 8. So we choose 8 most relevant experts. And then what we do is we see output of each expert, and then multiply output of each expert with the relevance of that expert. So so this output of this expert times its relevance, for example 0.4, plus output of this other expert times the relevance of 0.2. So outputs will get added up, but they will be weighted by their relevance. So experts that are most relevant will have a higher contribution to the output when we add them up. This is that formula here. So first of all, this ut is what the vector that we get from attention mechanism, so the vector that's passed through this mixture of experts. So this ht is what we get after this feed forward mixture of experts layer. So this is what we get from it. So what we get from it, and let's for now ignore this guy. I will explain this last. So first, we pass this input through shared experts, ns number. So from 1 to the number of shared experts, we sum up output of each shared expert. So this denotes output of each shared expert. So we have this function, which is a feed forward function. We pass in input, So this will mean output, and then we sum up all of the outputs. And we do same for routed experts, for selected chosen experts. So from 1 to the number of chosen experts, we pass in this vector. But important difference is that now each output we multiply by the relevance of the expert, by the score, the value of the gate that shows how relevant this expert is to the task. So this will basically scale down less relevant experts more. So they are contributing less to the final sum. And this is a residual connection. So when we process all of this, we also add this input, just raw input that we got after the self-attention mechanism. We just add that, it's same as this one. This is to preserve necessary information that doesn't need to be or shouldn't be processed or changed. So the neural network will figure out what the necessary information is. So it will adjust these things, so this FFN, FFN, so that such that when these results add with this guy, it will all come together and be good. And this is how we calculate those gating values. We start from the bottom here because they wrote the first equation at the bottom. We have our input and we transpose it. This input has batch size, sequence length, and dimension shape. And we have this expert centroid vector. So what is expert centroid vector? So a centroid vector is a learned representation that acts as the specialization signature of an expert. Each expert has its own unique centroid vector that encodes the type of input it's best equipped to handle. This is a learned set of weights that shows what this expert is good for handling, for doing. And so we multiply that with the transposed input vector to get some dot product. To actually we sigmoid will convert it between 0 and 1. The second equation, what it will do is for each expert it will either assign 0 a score, so that expert will not be chosen, or some other score that will be used later to multiply the output of that expert. So this is basically doing two things. It's selecting which experts are going to be chosen, and it's also assigning those scores to the experts to be later, so their outputs are later multiplied with those scores. So if score of the expert I and token T, or a vector embedding that came from token T, is in top K highest affinities, highest scores. K can be any number, for example 8 highest affinity experts for a particular token. So then we get top K experts that are selected. So each of these experts will have some affinity score between 0 and 1. But now we want to make those affinity scores add up to 1. So later, when we multiply output of those experts, in the end, we get 100%, that is 1. So to do that, we will take these raw scores and we will divide them by the sum, each score by the sum of the scores. After that, all of the scores for all top K experts will add up to 1. So I think now we can code this. But before that, there is an issue with this whole expert system. What happens is that router just starts favoring 1 or 2 or 3 experts and sending all of the tokens to those experts. Because randomly some experts will become better. And so router will just keep sending everything to them, and they will just be used for everything, and other experts will be underutilized. This is not good because you are wasting a lot of potential computation and storage and processing power of other experts. Solution to this from 2021 was that you train another smaller neural network that learns to evenly spread experts, not just to use one. But the problem there, now you are training a smaller neural network with a different loss, and that takes from computation for this our transformer, our DeepSeek transformer. So DeepSeek team came up with a different idea. You basically count how much each expert gets called, and the more it gets called, you decrease the probability, the affinity score that makes it probable to be called. And if it's called too few times, too little, then you increase probability that it's going to be called. So they just count how many times the experts get called. And they say that this not only improves performance because you don't need to train another loss or another neural network, but it also, they say, performs better than if you trained another neural network, maybe because it's simpler. Here they have similar mathematical formula, but this solution with bias is implemented. Here, where we have affinity score that's going to choose the top and top k experts, we are going to add this bias. So if expert has been utilized too few times, too little times, then this bias will be higher positive value number that will increase the chance of this expert being utilized. But if this expert has been utilized too many times, then this bias will be a negative number that will decrease the chance of this expert being utilized again. And the important thing to notice here, this is the probability for choosing the expert. But when we multiply the output of the expert with this score, we don't include in the bias. The bias is just included in choosing the expert, but the output is multiplied with the original score. So they have this hyperparameter that's called bias update speed, and they denote it as gamma. So during training, if the expert is overloaded, they will decrease bias by gamma. So bias is smaller, so it has a smaller chance to get selected. And if the expert is underloaded, they will increase bias value by gamma. On every step, they find it underloaded. But this is only updated after every batch. So within a batch, there is multiple sequences. So this might be too slow because within a single sequence, there could be unbalance. So within a context window, there could be like just a few experts called within tokens in that context window. So we also have complementary sequence-wise auxiliary loss. So we will start with this one. We have affinity between this expert and this token, and we divide that with sum of all of affinities of each expert for this particular token. So what we will get is each affinity will be scaled such that all of the affinities for this token add up to 1. So this SIT will be affinity of the expert I to token T, such that all of the affinities of every expert adds up to 1 for this token. This is just so we normalize affinities and we put them in perspective to each other. Then we take that normalized affinity between this token and expert, and we sum up for each token. So we calculate this affinity between this expert and this token for each token. And we divide by number of tokens. So what we get is average affinity between this average affinity of this expert, average affinity this expert has, expert I. That's gonna be pi, the average affinity. This fi is counting how many times the expert I has been selected. So first, for each token, if the expert is selected, you add 1. If it's not, you don't add 1. So for each, let's say 100 tokens selected 20 times, this would be 20. Then this is number of routed experts. So this is the total number of routed experts. This is the K is the total number of selected experts. So this can be, for example, 8. And we have, let's say, 32 total routed experts. And T is the number of tokens. To understand what this guy does intuitively, let's first see what would be ideal case. So ideal case is that we have total selections. So we have a fair share for each expert, and so each expert gets equal number of selections. And how to calculate this number of equal selections that each expert gets? It's a total selections, so that would be number of tokens times number of selected experts per token. That would be total number of selected experts. And we divide that total number of selections to number of experts. And that's how we get how many times each expert should be selected ideally. But here you can see that this is inverted. So this is, here we are getting 1 over fair share for each expert. So if each expert should be getting like be selected 5 times, this would give us 1 over 5. So we get the actual number of times this expert has been selected over ideal number of times it should be selected. So fi is going to be actual selections over fair share. So what this means is if fi is 1, expert I is getting exactly its fair share of selections, how many times it should be selected. Everything is divided equally then. But if fi is 2, then expert I is being used twice as much as its fair share. So this means, so fi will show how much more is expert I being selected than in a perfectly balanced situation where each expert is selected equal number of times. So now we put this fi number here, and to remind ourselves what pi is, measures the average normalized affinity for expert I. High value means tokens are strongly routed to this expert, so tokens have a high affinity with this expert. So I guess then since we are multiplying these two things and then adding them for each of the routed experts, if we ignore this alpha for now, that means that the more some experts are selected too much, the higher this value will be. It will, so this has quadratic scaling, I think. So so the higher value this will be, the worse it is. But I'm not sure, they didn't explain what they do with this then. So I think we will have to look at the code, and we will start coding now. And also this alpha is a hyperparameter that will minimize this, multiply it with like 0.01, so it's not too strong, it doesn't mess the other main loss that we are training for. We will create this class gate NN module. So the description, this is the gating mechanism for routing to mixture of experts. Then we have some attributes. Dimension, input dimension, this could be batch size times sequence length times length of the vector, the embedding vector. And then top K, number of experts we are selecting, and groups. So if we have like 64 experts or 128 experts, then it will be a bit too much to select from all of them at once. So we will divide them in groups. Just like we are dividing experts, we will also have groups. Let's say 8 groups, and each group has how much? 16 experts, I think. Yeah. So we will first select a group based on the token, so the token that fits the group. Also, same as we select the experts. So we will select top K groups, and then within those top K groups, we will select top K experts. So it's just the same thing 2 times, like in a hierarchy. Top K group, so how many groups we are selecting. Score function, is it softmax or sigmoid? This is to make scores between 0 and 1. Route scale, so once we get the scores, maybe we want to scale them to make higher scores even higher to sharpen them. Weight, this is learnable weights for the gate, so model will learn which experts, which tokens to route to, or which groups if we have groups. Bias, this is optional bias to the weights. So let's initialize, we will just pass in model arguments. If you remember, these are just a list of hyperparameters that will like have all of these things. So arguments, we will first super init, so initialize this super class and then module. So we will just assign all of the hyperparameters to these local variables. So all of the parameters. Here the weights are gonna be n parameter, and it will have these dimensions. N routed experts and dimensions. So this is the number of experts, this is the token embedding dimension. So you take a token or the vector embedding of that token that's juiced up with the context around it after the MLA, and then you multiply that token with this matrix transposed, so it will multiply that dimension, the token vector with this dimension, it's gonna be the same dimension, and what it will give you is an array of scores for each expert. So you see here you have number of routed experts, so you will get array of scores for each expert. But this may not be just the dimension of the vector. It can be batch size times sequence length times dimension of the vector, and it will work the same. So for each token in the sequence length, it will give you the number of routed experts for each token in the sequence length and batches. And then bias n, so this will just have the shape of n routed experts, so we will have bias for each expert if it's this dimension. So I don't know why they selected this dimension in particular. I guess you can make a different condition here. So we have then forward pass. This is the input tensor, and it returns tuple. So it returns routing weights and selected expert indices. So which expert are selected, the indices, and the routing weights for those selected experts. This is what it looks like. I can show you even more intuitively. So here, imagine this says sequence length. So we have batch size of 1, sequence length of 2 tokens, and dimension of 4 for each token. So this is 1 token, and this is second token. And here we have first expert, second expert, third expert, so 3 experts. And dimension of each expert is 4, just like this dimension of each token. So we will multiply, we will do dot product of this expert and this token and get some score. How well does this expert, how is it good to calculate, to use for this token? We will also do this expert with this token, get some score, and do the same for other experts and these two tokens. And that's gonna be our output. So here the scores are gonna be linear input times self-weights. This is what I just explained. Then if self-score function is softmax, then we will say scores equals scores softmax on the last dimension. So what this will do is it will make each token, so a token has a list of all of the expert affinity scores. So token has list of the first score shows how much affinity with the first expert, second, etc. And softmax will make those scores add up to 1. But if we have sigmoid instead of softmax, we will just apply it, and the scores will now not add up to 1 necessarily. So we will later divide them by the sum of them to make them all add up to 1. So we will manually make them add up to 1. Depends on the function here. Softmax will have more uniform probability distribution, while sigmoid will have more peaked probability distribution. So maybe when you are doing a task, maybe if you are specializing your network for coding, then maybe you want to use sigmoid because you need more confident, more peaked decisions. We have then original scores is equal to scores. We set them here. This is me from the future. So while I'm explaining the code for the gate, you see this bias? I'm going to refer to this bias as the classic bias from neural networks that you add to the weights and stuff. But it's actually not that bias. This bias is from their formula. So this bias is what they add to scores or subtract if this expert has been selected too much. So keep that in mind when I mention this bias. I forgot to mention that until later. Let's see the next part. So if self-bias is not none, we will just add bias to the scores. So if groups is more than 1, we will say scores equals to scores dot, and we will reshape the scores. So what this will do, I'll show you. First, in the beginning, the scores will be like this. It's just an array of these vectors. So expert 0 group 0, expert 1 group 0, and here expert 3 group 1, expert 4 group 1. So then what this line will do is group the scores like this. So make a group here. Group 0 scores for the first input, group 1 scores for the first input, and group 0 scores for the second input. So we would just, for each token, input token, we would have for each group the scores. So we have 3 experts per group. These 3 experts for this token, these 3 experts in this group for this token, for the same token. And then for the second token, we have the 3 experts from the group 1 and the 3 expert scores from the group 2. Then, if there is no bias, we will just calculate group scores. So we will use scores.amax amongst the last dimension. So what this will do is, I will show you. So here we have 2 vectors. The first vector says max scores for each group for first input. So we take a look at the first input, which is this. And in this group, the maximum score is this. In this group, the maximum score is this. So now we see that for this token, for the first token, the second group has higher score. So maybe the second group of experts is more relevant and should be selected. But if we do have bias, we're gonna use a bit different method of selecting. So group scores. So group scores is gonna be equal to scores dot. So I will explain top k 2, last dimension 0 sum. So we will take here, I will show you the scores again. So these are group 0 scores for the first input. So expert, first expert, second expert, third expert. And we will take top k, so two highest score experts and add them up. So 0.17 and 0.10. And that will be the score for this group. So this will be the score how this group is relevant to this token. And same here. We take the highest scoring expert and the highest scoring expert for this group, for this token, and we add them up. So that's the new score. So now you see the group 2 got score 0.33 and the group 1 got score 0.27. So the group 2 has higher score affinity with this token. Maybe group 2 will, or it's group 1 in this case, would get selected. This method of selecting the scores is more robust because now it's not selecting group that has like one very highly scored expert. It's selecting a group that has multiple highly scored experts. So now when you pass the token to the group, from that group, you can select experts. There is multiple high score experts that you can select and ignore all of the lower experts. But if there was, like in the previous selection method, there can just be like one expert that's high in the group and it would carry the whole group. But then when you are selecting from experts within that group, there is just one that's like good expert. So now that we have the scores for each group, so how much each group is relevant to the token, then we will select the top k groups to choose experts from. So top k most relevant groups. Group scores.topk, so this will select top k, and this will determine how many groups. So let's say we have 16 groups, we want to select top 4 most relevant groups. And this one will give us indices of those groups because we don't want the values, the scoring values of the groups, we want just which group by index. And later we will go within those groups and select experts. So we just need to know which groups. Then we want to create a mask of true or false depending on if the group is selected. But the true will be for the groups we want to exclude, and the selected groups will have false because we don't want to exclude them. So mask is scores dot new ones. This is the batch dimension, and so for each batch you have number of groups. So now we will just fill everything with true, and then after that, so depending on the index of the selected group indices, we will set those to false. So we don't want to exclude them later. And one, you can read all of that here. Maybe it's even better explained. One means we want to operate along first dimension, so the group dimension. This is an example. So if we have two groups and want to select one best group for each token, so indices of those selected groups will be the following. For the first token, we will select the group with index 1, which is second group. And for the second token, we will also select, for example, group with index 1. And the initial mask will be true everywhere to exclude all groups. And then after this scattering, we will replace second, so the group with index 1 and the group with index 1 for the second token with false. Next, we want to get a vector that has all of the experts from the beginning without any groups, and just experts that were in the group that was excluded, we want to exclude them, and experts that were in the groups that were not excluded, we want to keep them. So scores mask fill, mask unsqueeze. Okay, so let me write this, and then I will explain on an example what each of these parts of the code does. So here mask unsqueeze -1 adds a dimension to match experts within groups. So this is saying, for example, exclude true for this group, and then it will actually be converted to this there will be one more dimension, and this will say exclude true for each expert individually, and exclude false for each expert individually in this group for this token. And then flatten one. So this float minus infinity, this will replace the probability of this expert getting selected to minus infinity with minus infinity. And then we want to flatten them back to collapse group back into the flat list of experts. So example, in the group 1, we have each expert has these scores. And in the group 2, each expert has these scores. And then we will replace each of the scores of the first expert with minus infinity because we want to exclude this expert. So that's what we will do here with this unsqueeze and float. And then we want to flatten, so we want to remove this group dimension and just have everything like in a list. Now we have all of these experts like that. So then if we code the next guys, so it's gonna be indices. Now we want to select top k experts. So torch.topk, we give them the scores. We say how many top k experts we want to select amongst last dimension, and we just return index. So what this will do, so this top k will return, here you can see values and indices, so value and index of the expert it selects. But we just need index now. So we want to take 1. Okay, so let's see how an example for this. We have our scores that are minus infinity, etc. And then there is 0.19, 0.13, and 0.14. So if we select 2 experts, we will select 0.19 and 0.14 because they are most likely highest scores. And then because we are extracting indices, we will get 3 and 5, expert 3 and expert 5. The reason we take indices is because we added the bias. If you remember from this equation that I was explaining, we add bias if this expert was selected too much to the score. So we reduce the score. We add negative bias. But when we are multiplying the output of the expert with the score, we want to use the original score. So now we will take these indices after we have picked the most likely experts to get the original scores, because now we need the original scores. So weights is original scores gather indices, and this one will target the score dimension in the original scores. So we extract the raw scores. And we also, even though these are scores, we call them weights because first we need a different name. We already have named scores, but also these are the weights because we will use these things to multiply the output of each expert with the weight, with the score of that expert, with the relevant score. So then if the function was sigmoid, remember that we want the scores to add up to 1, which they weren't previously. So we will just make them add up to 1 by dividing them by their sum. And then maybe we want to make the weights sharper, or so we want to make higher weights, maybe like experts that have higher weights contribute more to the output. So we can do this scaling if we want to. Maybe this would be good for tasks like mathematics coding, where we want to put real experts that are best at it to have more weight, while in creative writing maybe we want to get a bit of every expert. So return weights type as x. Yeah, so we will return weights in the shape of x input that has like sequence length and weights. and the indices of each expert that this token will get chosen for. So that concludes our gating network. Now we can continue with implementing a mixture of experts. Next, we will code experts. So each expert will be a multi-layer perceptron or neural network. Okay, so let's start from here. Class MLP, and then this will be a feed-forward network, so each expert is a feed-forward layer. The first attribute is the first set of weights, W1. This will convert from our input vector, and remember, this input vector is of size token, but it's a token that's been added with all of the context around, with all of the tokens after the self-attention layer. So this expert is gonna take that vector that has all of this context, and it's gonna find out which features are more important from the context. It's gonna exaggerate them, and which features, which parts of the context are less important, it's gonna maybe diminish them. And also it will figure out what to do with all of this context, how to transform it, what is the task in the context, what to do with it. So I will show you here. So the first, this array, this vector, input vector is what we get, and this W1 set of weights will transform it to this hidden dimension. The hidden dimension is always in these experts a lot wider, bigger than the input token dimension, even though token dimension is very big as well. But the hidden dimension holds a bunch of information from the internet, holds different rules on how to process this input that it learned, etc. Let's go this next one. The next W2 will convert hidden to output. And we will have output vector. Here in the image it just shows one number, but we will have output vector, so hidden to output. And the W3 will also convert input to hidden. But W3 will help W1. And together they will learn different things. Both will convert input to hidden, and then the product will be I will show you how the product will be multiplied later, but the important part is they will help each other learn they will learn different things and help each other. If we continue, we will define initialize method. This will take the dimension of the input vector and the inner dimension, hidden dimension. So the dimension of the output will be same as dimension of input, so we don't need to take that. Initialize this MLP layer, and these are the two arguments that I just explained. Input and output dimensionality and hidden layer dimensionality. We will initialize super, so NN module. So we now create the W1 vector. Now let's imagine this has linear, because if we have just one GPU, then this will act as a linear layer. And I will explain, after I finish this, I will explain how parallelization works, although I already explained this before, so I will just repeat it a little bit. And W1 will have dimension as input and interdimension, hidden dimension as output. It's going to convert from this to this. W2, this will be row parallel, but if we have just one GPU, it's going to be same as linear. And the input hidden dimension or inter dimension, which is hidden dimension, to the output dimension. And W3 will also convert from input to the hidden. Then we have forward layer, so this will we will get X torch tensor. So this is the forward pass of the MLP layer, and this is the input tensor. So I believe input tensor will be batch size times sequence length times vector size for each token. Output tensor, so it will return the same size as the X input, but each vector each vector that's corresponding to a token will get processed and by this. So this is just one forward. It's very simple. So let me write the whole thing. So we pass the input through weights 1. We then pass that through the SILU activation function, which introduces non-linearity. And then we multiply that with weights 3. This is a good explanation here. So first, both W1 and W3 extract different feature sets from the input. They transform the input in a different way. And then SILU applies non-linearity to W1 pathway. So you know SILU function. It's going to, if the values are high, it's gonna basically pass them. But if the values are low, it's not gonna pass them. It's gonna actually reduce them a lot. And I think they will never be 0. They will just be reduced a lot. So we will basically have this dampening effect as opposed to using ReLU. And then multiplying these SILU activated features with these features that are not passed through activation function, this would then serve like a weighting factor for these features. So what that means is it would amplify important features when both pathways agree, suppress irrelevant features when either pathway produces values near 0, and create complex features interactions through the multiplication. So then W2 will convert from whatever we get here as the input dimension to the output vector. And this architecture is proven in transformers to learn better than if we just had W2 that's processing activation function of W1. Because this allows, this gating mechanism allows for more complex feature interactions and better control over information flow. I explained earlier, but maybe I can quickly repeat. Column parallel, each GPU will receive full copy of the input, and it will just generate one part of the output. And in the end, those parts that each GPU generates, they add up to make the whole output. So each GPU here will have its part of the conversion projection matrix. And in row parallel, each GPU gets part of the input now. And each GPU generates the whole output. So different GPUs will generate different whole output, but with different features, different parts of the input. And in the end, every output will be added so that the final output depends on each part of the feature. These two methods of parallelization are used here. Then the expert class, so this is the expert class, is exactly the same as MLP class. Just one change here, they are not using parallelized linear layers, they are just using linear layers, unlike here. Then we will create mixture of experts class. Here we will combine the scoring function, MLP, experts, and everything. Mixture of experts attributes, the dimension input, the input vector from the self-attention, number of routed experts, number of local experts per GPU, number of activated experts, gate, this is the function, and we'll see what this number of activated, so experts is a list of module list, so a list of expert modules that we defined here. And the shared experts, it's also a list of modules that are shared experts. I think we will define, we will define these in the init, and we'll still see what this n activated experts, number of activated, so I think n activated experts is how many out of routed experts are selected. So we have in total 64 and we select 6. We select number of activated experts. But we'll confirm this later while we code as well. Here in the int, we will going to have just initialization. Then we just give these attributes. So assert that number of routed experts is divisible by world size. World size, if we have one GPU, it's 1, so it will be divisible. Number of routed experts, local experts, so total routed experts divided by world size, the number of GPUs, will give local experts per each GPU. Activated experts, expert start index, so rank is the number of the GPU. So the first GPU times 4 experts per GPU, for example. So expert start index, this will just tell you the expert index of the first expert at a certain GPU. Expert end index is start index plus n local experts, so this will give you number of experts at a GPU. Gate, just initializing gate. And then we initialize experts. So this will be nn module list of expert that we defined. The same you already know the dimensions. If start index from start index to experts end index, else none for I in range n routed experts. So creates a list of all experts, but each GPU only creates its own experts and puts none for other GPU's experts. Like GPU 1 creates these experts but puts none for other experts. So for I in number of routed experts, it's gonna create expert if I is between expert start index and expert end index, or otherwise it's gonna say none. Then we have this MLP, these are shared experts, multi-layer perceptron, and dimension to n shared experts times MOE interdimension. So this MLP will be one big block of shared experts, and it looks like this is gonna be a more computationally efficient because now we only have one input dimension, and all of the output dimensions are kind of concatenated and calculated together, all of the expert outputs from the same dimension. And in MLP we are using the parallelization. Continue. Let's define forward function. Forward passed with MOE module. X, the input tensor, that's batch size, sequence length, vector embedding length. Save that shape for later. And then what we want to do is, instead of having batch size, sequence length, self dim, we just want to flatten batch size and sequence length. So we have a big array of just token or the vectors. So we just have this big array of vectors, and we will pass one by one through the experts, and that's it. So this is the gate. We will get weights and indices. I explained this earlier in the video. We will create this Y to store expert outputs. Then we will count how many times each expert is chosen. For example, expert 1 is picked 5 times, expert 2 is picked 3 times. This min length makes sure that the minimum length is the number of routed experts, so even if some experts are not chosen at all, it will assign 0 to those experts. Then we have 4 I in range experts, index start to experts index end. end index. So it will iterate through each expert that's assigned to this GPU node. If expert has not been selected any at all, then we just skip it. And then if expert has been selected, we will get this expert model by the index. So let's say we have this kind of tensor. So input 1 gets expert 0 and 2. So this is the token 1, the vector embedding 1. Vector embedding 2 gets experts 1 and 3. Now we do torch where indices is equal to I for different experts. So for expert 0, we get the index and top k. Here you can see that input 1 and input 3 use expert 0. So the indices are 0. The 0 is the index of the token 1, of the first token. And 2 is the index of the third token. So we get indices of these tokens for this expert where this is the 0 expert. And we get 0 means this expert was chosen to be the highest, the first expert. So 0 is the index of the first expert that's chosen, the highest affinity expert. And in both of these, it's chosen as the first expert. After that, we have, this is the output of the expert. And we are saying plus equals because this output might be affected by multiple experts. So whatever we have here, we will just add the output of this expert as well. Because as I said, each vector embedding is processed through multiple multiple routed experts, and we need to add up their outputs. You can check here the number of the shared expert, the routed expert, sorry. So we pass in the input through the expert and weight it properly. So it will be weighted by the gating value, if you remember. And this is just to select the weight using index and top. Then we will pass the input through shared experts as well. We will get this Z. If there is more than one GPU, then we need to combine all of the outputs of the experts on different GPUs. So for example, a single token could be sent to one GPU for a few experts and to a different GPU for another few experts. And now we need to combine all of them. And here it says return Y plus Z, so this will combine shared experts and routed experts. And we need to say .view to shape, so we will return the original shape that was batch size, sequence length, and the token and the vector embedding. Then we will code the transformer block. So block contains the attention mechanism and the MOE, and then blocks are stacked after each other like layers. So class block and module, and I will just skip it, it's easy. So initializing layer ID, layer index of the in the transformer, so this is a layer or block, it's just repeated n times. Initialize super. Okay, so we define attention, MLA, and pass in arguments. We define feed forward network, which is MLP, if layer ID is less than number of dense layers. So in the beginning we will have just one dense layer here, or we can have multiple dense layers before we have MOE. Early dense layers can be seen as extracting features or processing features in some way before we start using experts later for each kind of feature. That is for each token with different features. Then we just define normalization This is attention normalization and FFN normalization, and then forward pass. X is the input tensor. Start position, this is start position, the key value cache for our MLA, where to store the keys and values and where to read it from and stuff. Frequencies, cis, freaks, cis, this is the rotations, rotary embeddings we need to apply to the vectors in the attention mechanism. I explained this earlier in the video, and mask for the attention mechanism. It's just explanation of everything. So we pass in X through self-attention, to attention normalization, and then that we pass through self-attention and we give it the key value cache, start position, and masks and rope, and then we have a residual connection here. Then we just define normalization. This is attention normalization and FFN normalization, and then forward pass. X is the input tensor. Start position, this is start position, the key value cache for our MLA, where to store the keys and values and where to read it from and stuff. Frequencies, cis, freaks, cis, this is the rotations, rotary embeddings we need to apply to the vectors in the attention mechanism. I explained this earlier in the video, and mask for the attention mechanism. It's just explanation of everything. So we pass in X through self-attention, to attention normalization, and then that we pass through self-attention and we give it the key value cache, start position, and masks and rope, and then we have a residual connection here. You see here in the transformer architecture, you see here self-attention mechanism, and there is a residual connection that just adds here to the output of the self-attention. This is because besides processing it with self-attention, we also want, when we add it, we keep some of the original features, and so they are unprocessed, and we keep those original information untouched. Maybe we need that as well. So then we normalize X again, and we do normalization before the layers. It turned out to be better that way. I think in the 2017 paper they normalized after these layers. Okay, and then pass through the FFN, and then just return X. So that's gonna be block, or one layer of the our DeepSeek R1. Now we will add model arguments here on top of the file. So this is gonna be what we already talked about, a lot of them. Max batch size, you know all of these, what they mean. So I'll just skip through them quickly. And expert groups and limited groups is top K groups we are selecting, that's it. So all of this should be familiar with you. And then we have beta fast and beta, actually we have theta also. Rope theta, this is the fixed angle by which when we are applying rope to vector embeddings, to token embeddings, how we are rotating by this angle. And beta fast and beta slow is scaling. I said before that the first pair of dimensions rotates at a certain speed, and then the last rotates at a different speed, and it's interpolated between. So I said before that the first pair of rotation rotates slowly, but I think the first pair is rotating the fastest here. No, actually Claude says the first pair rotates slowly, because this is the frequency formula. So you can see what's the case. So I think the first pair is slow and the higher pairs are faster. M scale is the scaling factor for the extension, extended attention. We just apply all of these. So they are what we already explained. we were gonna use softmax for score function in MOE. This is the score function for the gate. All of this we talked about. Yet another rope extension. Yeah, that's it. I think we all understand all of these parameters. One issue we're going to have is DeepSeek only released inference code, so this transformer class is for inference, but we can understand how it works and we can understand how we would adapt it for training. Let's start by coding class transformer that inherits from NN module. So we're gonna have some attributes here. Sequence length, this is context window, embedding dimension of the token, number of layers, each of the, so one layer is like MLA and MOE together, and then how many times you repeat that. Normalization layer, and then module, this is the head, so this is from the last layer. When you get output from MOE, whatever the token embedding is, you want to convert that into probability distribution over all tokens. So one guy into all of the tokens probabilities to choose the most probable token or something like that. Some of the most probable. And frequencies, this is for the rotary embeddings pre-computed, so each position and each in the sequence and each position in the token vector, how they should rotate. Then this will be a lot of just initialization. So we have world size is the number of GPUs and the number of the current GPU. Is it 0, 1, 2, 3? So get world size, or it's 1. So we will just get the world size number of GPUs. Rank, it's gonna be 0 if there is only one GPU, because this is gonna be just a GPU with index 0. So, or we will just get the index, the rank. Type of linear layers. So we're gonna, if this, we're gonna set it to FP8 or brain float 16. Initialize super, and then set these parameters: max sequence length, parallel embedding. So they defined this class. This class is defined in their code. So each we will define a bunch of layers, and each layer will be this block, and the block consists of MLA and MOE, mixture of experts. Then define RMS norm. This is the output head, so you are converting from the dimension of the token from the last MOE layer into the vocab size. Register buffer just for saving these non-trainable parameters in the memory, the frequencies, the rope frequencies. We can continue. Now they have this storage inference mode, which we will remove later, but let's first I will show you the code that DeepSeek released. So we have forward function, it has tokens, this is batch times tokens, and there is no vector embeddings for each token. It's just a list of context windows, multiple context windows. And start position is for the rope scaling, I think. We'll see here. Start position, starting position in the sequence for rotary embeddings, defaults to 0, yeah. And returns logits tensor of shape batch size vocab size, so it returns probability for each token to be selected, and then batch size of them. So you have a sequence of tokens as input, and this will just return for the next token the probability distribution of each or everything in the vocabulary, every possible token in the vocabulary. So even though you will get a sequence, the whole sequence length, a bunch of tokens as input, you will just get one token as output that is not the token but the probability distribution for that token. And there will be batch size of those next token probabilities, just like there would be batch size of the sequence length of context windows, and they are all independent. then we will get the size of the sequence length. So token size 1, it's a bunch of sizes. And then we will embed tokens. And then we will get these rope embeddings frequencies. It's always the same function. I always explain the same thing, yeah. Mask is none for now. If sequence length is more than 1, then we are creating this trill function that will mask future tokens. It's gonna look like this. Here you see minus infinity on this triangle. So then for layers, we will pass these tokens, embedded tokens, through each layer and pass in some rope parameters. Then we will just select the last token after this normalization so we can use it. Although it's not really last token, it's a rich representation with all of the context from MLA, from mixture of experts and multiple layers. So we're gonna just get this last token that's enriched with context, and we will push that token through the head to get a list of probabilities for each token in the vocabulary to select from. So if you have a distributed training on multiple GPUs, you can write more, you can read more here on the side, but you will just gather all logits from different GPUs and concatenate them. And now you have one big vector that shows probabilities for each token in the vocabulary. And in the end, just return logits, and that's our transformer class. Then we can take a quick look at the main function where they invoke this. We just set default type, we set this to CUDA to GPU, some random manual seed, and then we initialize model arguments. Here they simulate tokens by creating these random numbers. So of batch size 2 and sequence length of 128, they just make these random numbers. And then model is transformer, pass in arguments, and they can print in the model size. Now let's see how Claude 3.7 thinking would adapt this transformer class from inference to training. I don't know why it would remove all of the attribute descriptions, but I wouldn't. Okay, so it moved this inference mode down below. So we have these targets. That's additional parameter to the forward function, which just shows the target token you are trying to predict, or the transformer is trying to predict, so you can calculate loss between target and the predicted one. Okay, so we have inference mode and training mode, and in inference mode the return is the same, but in training mode it's gonna return both logits and loss, and it will have size, batch size, sequence length, and vocab size. So for each, not just for the last token, the predicted token, but for each token we will calculate the logits and the loss. Because of the training, it would take both batch size and sequence length, not just sequence length. And then it would apply dropout during training. Maybe this is not, I think some of the transformers don't use dropout, but anyways, it would just move this inference thing down below. So you see here, if not self-training, and then does this inference code. And it would just apply this normalization in the step before, so it works for both inference and training. And so during training, compute logits for all tokens instead of just the last token, the predicted token. And the parallelization across different GPUs works the same. Yeah, it looks exactly the same as here. Compute loss if targets are provided. So loss none if targets are none. So if targets are not none, so if they are provided, then we will use cross entropy loss. So here is a better example of what these two lines do. Let's say you have a sequence ABCD and you calculate logits for each, so probabilities for each of the tokens. During training you do this. And then you also have targets BCD and end of sentence or end of sequence. So what these two lines will do is they will shift in such a way where it will remove the last here token. So you see here you take every except the last one, and here you will remove the first token, so it just removes the first token, starts from the second one. Contiguous just defines what type of memory this will be stored for PyTorch to use. And then what does this scary cross entropy loss do? So let's say you have batch size times sequence length times lookup size. With this view operation, we will make it batch size times sequence length and then lookup size. So instead of having tokens separated into sequences and then batches, we will just combine sequence and batch dimensions, and so we will just have a list of array of tokens, and that's it. And we will do the same for the targets. We will just convert it into array of tokens. So then this cross entropy loss compares probability distribution that's generated versus target one that should exist. So the cross entropy loss is optimizing for generating the correct probability distribution. And below that it just defined inference function. So torch inference mode and then the forward, and that's it. Thank you for watching this course. You can check my other videos if you want to learn more about AI science and engineering and research. You can also support me and help me do this full time so I can spread this education by supporting me on Patreon. Goodbye.